information they are using and other data sources, and what kind of climate services the Estonian Environment Agency has. So Tarmo, please.
So good morning to everybody. Hopefully you have had a nice morning so far, and I hope that today's and tomorrow's seminar will be very interesting for you. So as it's already said, my name is Tarmo Sulg. I'm a head of Weather Forecasting Department at the Estonian Environment Agency. And I have been working in this position for 10 months. So I'll try to be as accurate as this short experience allows. This is for the slides, yes. No. So how can I go on? Next. No. Maybe this back one.
Feel free to talk about yourself.
Yes, I have 40 minutes left, so I would like to tell about myself. Yes, my idea was to talk about how we are using freezing data of marine and inland water bodies in Estonia, why and for whom it is needed, and what data sources we use for this. Because Estonia's maritime border is about 3,800 kilometers long, including the islands and winding coastline. Can I try now? Yes, I think it's the perfect slide. Yes, it moves now. Yes, very good. The coastline of the continent alone is 1,240 kilometers long. And in addition, there are approximately 1,200 larger lakes and 7,000 rivers and streams in Estonia. About 2/3, nearly 65% of Estonian population lives in coastal areas or near the sea. And this means that sea and ice conditions affect a large part of the population daily through the transport, work, recreation, and nature. A few words about myself and about the Estonian Environment Agency. The official start of the national weather services in Estonia considered to be 1919, when the Central Meteorological Institute was established. Its core role has remained essentially the same to this day. Today we are operating as an Estonian Environment Agency. We have approximately 200 employees, and the organization consists of 6 departments, each named according to its core functions. And our functions are national environmental monitoring, weather forecasting and climate analysis, environmental data management and reporting, forest, air, soil and water assessments, and supporting evidence-based policymaking. As the head of weather forecast department, my responsibilities are general and aviation meteorology. We operating automating observation systems at 4 regional airports. And at Tallinn Airport, we have also on-site weather observers. My department oversees the development of numerical weather prediction models, the IT solutions necessary for operations, and the services we provide for our clients. And during the ice season, ice service duties are divided by the people from the different departments, 2 to 3 weather forecasters, and 1 remote sensing and GIS specialist. In Estonia, the freezing of the sea and inland waters in winter is a common natural phenomenon. As a northern country, ice cover of lakes, rivers, and sea is critically important service for our residents and clients. Composed ice maps provide information on both ice thickness on inland waters, which is measured and uploaded by the rescue board, and the formation of sea ice composed from different data inputs by the Environment Agency. Reliable and up-to-date ice maps are important for many people. First, to ensure safety, the ice map shows where the ice is strong, weak, or dangerous. And this helps to prevent accidents for both people, vehicles, and ferries. Secondly, it's important for the safe organization of passenger and freight transport with islands and also internationally. The ice map is necessary to determine the ice conditions for the operation of shipping lines and to decide when to start providing icebreaker services in our ports. Thirdly, also rescue services and border guards use ice information to prevent dangerous situations and to respond to rescue events. Fourthly, ice conditions affect the safety of recreational fishermen and ice sports in wintertime. And fifthly, changes on ice conditions show the impact of climate change in the Baltic Sea region, which is important for developing a long-term view, composing a climate atlas, and assessing environmental impacts. For example, we know that when there is a less ice cover, winter storms have a greater impact to our coastal area, which changes rapidly due to erosion. Here you can see our main partners. As example, Estonian Transport Administration is using the sea and inland waters ice information to ensure safe winter navigation and effect planning of the ship and ice-breaking routes, which also helps to prevent shipping accidents risk and oil pollution during winter. And in some winters, ice roads also were opened for vehicles. Police and Border Guard Board uses ice info to ensure our citizens' safety on Lake Peipsi, in which we have a common border with Russia, and to avoid accidental drift of people into the territory of a hostile state and vice versa. And based on our rescue board's information, we are also providing restrictions going on ice, which is vital in certain weather conditions. Yes. This slide summarizes all the layers of information that we are using as an input for our ice map and ice report, which are monitored and used daily. And I will show them a little bit more detail. First, over Estonia, we have 4 observation stations. 3 of them are on the islands and 1 of them on the mainland. Observers monitor and measure ice every day during the ice formation period. In addition, we have created opportunities in our weather app Ilm Plus to enter data on inland water bodies to the rescue board, and volunteers can also enter information from any water bodies. In the last season, over 500 entries have been made about ice monitoring. And the added value for us is the people's interest and awareness of ice conditions. As one of important inputs, we use Sentinel-1 SIR data, which is analyzed on our S-Tube platform. After 5 hours of satellite overflight, we have a map layer that we can use in data analysis. We also use RadarSat-2 data from 22-23 season. It is a very convenient data format that we can convert directly to the QGIS platform. The downside is image a little bit noisy, but the coverage of the area is very good. The best ice information with the highest possible resolution in clear sky conditions offer satellite products MODIS Terra Aqua, OLCD, and Sentinel 3A, 3B, and 2 MSC. All the operation data processed on the S-Hub. In addition, in clear sky conditions, WIR products GNB and SnowAge RGB are also very good for input. We also use Copernicus Marine Environment Monitoring Service products as needed. And in cooperation with Baltic, the identification of sea ice species and ice thicknesses with a machine learning algorithm has been developed to automate the analysis work. Unfortunately, this did not give good results and needs to be redeveloped and trained with larger amounts of data. All the above information is gathered in different dark layers in this GIS environment, which is our ice chart drawing tool developed by the Environment Agency. It is our daily tool for our people. We can check automatic data to decide on data quality, and if necessary, draw the ice contours and determine ice types by the hand. Ice chart can be exported to GeoServer and ice chart webpage. And the GIS platform also allows us to calculate ice statistics for certain time period and for certain sea areas. I still see that we have a lot of data, but a large part of the final finishing is done by the hand. Depending on the conditions, it takes 4 to 6 hours a day to compile the map. Public and interactive ice chart or ice coverage web application consolidates all essential information. The ice thickness of inland waters measured by rescue board, and the formation of sea ice according to the composer analysis. Estonian Ice Service produces daily marine bulletin, ice report, and ice chart. And they are distributed into the international network by the 11 UTC. Environment Agency also provides operational marine forecast to the public using regional NEMO-EST model configuration. Ice forecasts are produced on demand from customers. And during the summer season, the same application displays satellite images that can be used to monitor blue-green algae blooms. I have 25 seconds left. Okay. We also provide national ice statistics, overview of ice season, containing dates of ice formation and ice breakup. Here you can see that our last 2 winters were very different. In 23-24, there was a lot of ice. 24-25, there was little ice for a very short time. And it is also affected the length of the ice breaking season and the national expenditures on the service, as there was no need for ice breaking service in ports in 24-25. I also mentioned that we are preparing a daily marine bulletin to meet the international requirements, which is the basis for the organization of international shipping. We are producing ice reports for the Gulf of Finland and for the Gulf of Riga. Estonian Environment Agency is moving towards using different digital twin Earth applications. Today's operational services are related to Destiny E Extreme's DT initiative, and we are having ongoing developments and services as follows. Storm Surge Extreme Detection Service, which is pre-operational in SAMWF, Extreme Detection Framework. Also, Storm Surge Impact Model integrated for on-demand execution within Diode workflow, and application of sea level prediction models in Diode workflow, Hydra 2, and the NEMO EST 05 impact model. One of Environment Agency activities is also to compilation of climate atlas, which is also includes marine climate data. Sea ice climate projections until 2100 will be available via Climate Atlas. And today we can see that there will be significant changes in the future scenarios that we'll have to adapt to. For 2100, winter sea ice thickness values in coastal sea will reduce 30 to 50%. And sea ice thickness values are reduced till 20 centimeters. And sea ice maximal extent will be reached later in season. Also, sea ice decay period will be shorter, and some ports will be completely ice-free. For conclusion, the presence of ice and high-quality data about it helps to improve our daily lives and the national environment. To create safe conditions for our local businesses and residents, also for visitors and goods moving on the seas in the long term, we need information. To do this, we need high-quality data and a high level of automation. The Digital Twins project must create added value for data users and for assessing the future impact of today's decisions and scenarios. For example, the construction of wind farms or the protection of the coastal areas from erosion caused by the winter storms, which are brought about by changes in the marine environment. Thank you for your attention. I wish you an interesting seminar.
Thank you, Tarmo. Do we have questions, comments from the audience at this moment? Nikolai.
Do you have exchange with other services from the Baltic countries, or like everybody's working by themselves and don't talk to each other?
Yes, we are talking to each other and we have a very good cooperation so far. Thank you, but we'll try to get better. It's very important for us also.
Okay, thank you, Tarmo.
Thank you.
And now we move on to the next presentation. Nikolai already opened his presentations with a question, but now he can tell in more detail about cryosphere digital twin solutions. Please, Nikolai.
Well, 1, 2, 3. Is it working? Okay, so, okay, right. So thank you very much for inviting me. My name is Nikolai Koldunov. I work in Alfred Wegener Institute. And the title of the presentation is pretty long, but the idea basically is to tell you what the TerraDT project is about and give you a little bit more context about why we're doing what we are doing in TerraDT and what our plans are. So first, why the TerraDT project is needed. We have a Destination Earth program, and inside of the Destination Earth, there is a Climate DT, digital twins, which can be basically seen as the big, very high resolution models that produce simulations for support decision making on climate change. And you will hear about them a little bit more later in the presentations from, for example, Sebastian Milinsky. But these high-resolution models have their limitations, and they are kilometer scale models, so the resolution typically is like 10 kilometers or 5 kilometers, or even sometimes 2 kilometers. And one of the shortcomings is that some key components of the Earth system are not really present there. We have sea ice there, not ideal, but for example, things like aerosols or land ice is not really well presented there. So another thing is that the information relevant for some impact sectors is limited, so we try to address this as well. And another thing that those models are monolithically built, right? So they actually consist of so we call it one executable, right? So you compile everything in one place. So it's very difficult to extend them. And this is what we try to work on as well, is to be able to extend this model so that adding new components of the Earth system is easier. So this is basically what I said just now, new digital twin components, impact models, and modular software infrastructures. That's something that we work on in TerraDT. A little bit of information on the project itself. So duration is already almost a year in the project. So we have another 3 years. It's 18 partners and coordinating CSC IT Center for Science from Finland. Here is the composition of the consortia. You can see quite a diverse selection of different institutes. And as in, probably from the European projects, you have to have objectives of your project, and we have them as well. So objective 1, and which is related to my initial slide, is to build and deploy digital twin of the Earth system for cryosphere, land, surface, and related interactions, right? So we have a lot of gaps in our present digital twins, but we concentrate only on these 3: cryosphere, land surface, and related interactions, whatever it means, to provide improved climate projections and impact assessment to decision makers. So we will add the new components, in particular the ones that are interesting for us today is land ice and sea ice. We will develop also impact models linked to the information that we will produce with this extended digital twins. And we'll provide the multi-decadal coupled simulations with this new improved digital twins. And this is how it looks in practice. Maybe it's a little bit overwhelming for the people who see it for the first time, but it's not too complex. So we have core climate models. So one of them is ICON, another two is IFS Nemo, and the one that I'm working on is IFS FESM. We will have a coupling interface, so the additional layer that we will build in TerraDT, and we will couple land ice, sea ice, aerosols, vegetation, and land use, run the simulations with them, produce the information with these additional components, and this information will be used by the impact models. So as simple as that. Another objective is to develop a new infrastructure to extend destination Earth digital twins. So we will, I mean, it's a little bit more technical. I'm not sure that how interesting it is for most of you, but basically, again, as I said, right now we have monolithic software that is hard to extend, and we try to make a coupling interface in order to be able to extend it. And we also want to do the model performance improvement, and the application for impact models also have to be deployed through the Destination Earth platform. That is something that, well, I mean, also probably you will hear about in the next 2 days. And the system will be deployed on two very big, I think Lumi is still the biggest supercomputer in Europe. Maybe Jupiter is already overtaken it, but at least a year ago was the biggest supercomputer, and Mare Nostrum 5 is also pretty big. This is like the last schematic that I'll show probably. Again, so how we fit into Destination Earth, let's say, ecosystem. So the light blue parts is what Destination Earth produces right now. And we have core climate models, which are very high resolution, that are run periodically. They generate some data. There is some quality assessment. Well, I mean, the data are streamed, so they basically saved somewhere where you can access them for a short period of time. You can do quality assessment, do some applications, then they saved to something that's called data bridge, and from the data bridge, they go to the data lake, where they stored, like, hopefully forever. And from there, you can also develop some applications that are basically useful for the users. And TerraDT adds additional components through the generic coupling interface, right? Land ice, sea ice, and land surface and aerosols. And we have a couple of impact models that also work on different stages of the data that produced by the Destination Earth. And objective 3, of course, is to kind of spread the word about our great achievements, and through the impact and policy workshops, outreach materials, user stories, and adoption toolkit, and strategic alignment with Destination Earth. So we have to talk to Destination Earth a lot, and contribution to international collaboration effort. Basically, just to say that we don't work in our little silo, but we also open to the world and try to make impact as big as possible. This is basically like all the components that TerraDT having, and just the take-home message: TerraDT developed digital twin components, impact models, and models of true infrastructure to enhance Destination Earth digital twins, mainly for climate DT. All right. And inside of the TerraDT, we have so-called pillar 5 that is called cryosphere. So here we're coming to the sea ice a little bit closer. It's led by myself and Thomas Swinger from TSC, and here is our partners, and we have 2 directions: land ice and sea ice. I will talk a little bit more, much more about sea ice today, but there will be something about land ice as well. So I was talking about digital twins a lot, but what they actually are. So again, they are high-resolution climate models that consist on different components, and 2 main components is atmosphere and ocean. And this is one of them. It's called IFS FESM, right? So IFS part is basically the atmosphere. So you can see it here. It's overarching thing. And FESM is the ocean. And FESM consists of like ocean component and the sea ice component. We also have waves and land as part of this model, but most of the time we are talking about atmosphere and the ocean. And atmospheric resolution for the digital twins right now, standard one is 5 kilometers. And for the, like in the atmosphere, for the ocean, we have something that I will also talk a little bit more about in the next slides, the so-called varying resolution. So you can increase resolution in any part of the world. And this is how the resolution for the special resolution for the global mesh for the digital twin look like. So we have about 5 kilometers in the, like in most of the North Atlantic and in the Southern Ocean, and a little bit lower resolution in the tropical areas where you have a little bit less action from the ocean side. And like, since we are talking about the Arctic today, this is how the, in this case, it's 2.5 kilometer resolution digital twin results looks like. So the gray shading is U wind component, and you can see that you don't really have to even plot the land, because the difference between the underlying surface between the ocean and the land actually highlights the land itself very well. So you have not a strong wing over the land. And you can see underlying is the sea ice. And like people who know how sea ice in the Arctic looks like in the recent years can immediately see that we are not perfect with our simulations. But I mean, the level of detail, I think, is pretty stunning. And also you can see, I mean, it's already past this, but I mean, there are some cracks developing in the sea ice field, and you can see, well, I mean, that, like, at least from the visual perspective, the realism is quite good. Also, this resolution allows you to study some interactions between the sea ice and the atmosphere much better. So this is for the first time in the global coupled simulations where we can see effects of the sea ice leads on the atmosphere. So on the left-hand side, it's the sea ice concentration, and this darker areas is basically leads opening where the sea ice is not present. And you can see the temperature increase over these regions, over these like narrow areas. And also heat fluxes increase, and there is some effects on the atmosphere that are coming from these openings that was not accounted for in the previous global simulations, of course, because I mean, usual CMF6 simulations about 100 kilometer resolution. We are talking here about like I mean, in this case, I think it was 5, but we can go to up to 2.5 kilometer resolution. So a little bit more about FESM and its unstructured mesh. Let's see if we can run it. So this is how the mesh is organized, right, in the ocean. So atmosphere is uniformly, let's say, 2.5 kilometers. In FESM, we have a possibility to actually increase resolution where we want it to be increased. And for example, along the coast, you can see, I mean, that's not the resolution that we use in Climate DT. It's a little bit lower, but the idea is the same. So for example, along the coast, you have higher resolution. In the Gulf of Finland, for example, you can see we can increase the resolution, and it will be important like later on. In the straits, it's very important that instead of like low resolution that you have here, with just 2 points, you can increase it and make the flow of the ocean much better, right? And it's all coupled to the atmosphere. And there are 2 ways how you can exploit this this idea of variable resolution. One, you can have globally changing resolutions. Increasing resolution is the places where you where there is a lot of happening, there is a lot of eddies, for example, in the Gulf Stream and so on. Or you can have basically a regional model. It's still a global ocean mesh, but in the places like Arctic Ocean, you can have increased resolution. And the same thing can be said also for the Baltic Sea. In principle, we can have like a global model which has very high resolution regional Baltic Sea. What this allows us to do is to have global models with 1 kilometer resolution Arctic. And this is how temperature in this kind of simulation look like. So you can see there is a lot of details already in the Beaufort Sea and also here like in Eurasian Basin. And if we zoom into this area, so you should imagine that you actually in this region, but turn it upside down. So this is the Beaufort Sea. And you can see that there is a lot of also eddies and eddying activity that is going on in this area. So what about sea ice? How this type of model resolution allow us to see, and allow us to study the interaction between the ocean and the sea ice. So here I try to plot the sea ice as the light and transparent blue shading, and what you will see below as colors is the temperature. Again, that's the Beaufort Sea. This is from our 1 kilometer resolution simulations, and I mean, I don't know, you are experts here, and you can tell me if, the movement of the sea ice and the level of detail actually looks like what you see from the satellites, or it's not really. But at least we are pretty happy with the level of detail, and you can see that there is a lot of things that you can look at what are happening underneath the sea ice, how the eddies are interacting with the sea ice, and how the sea ice also behaves under the force, under different forcings that you provided in the Arctic Ocean. So that's I think it's pretty cool. And this is like a global view. Again, the 1 kilometer resolution Arctic sea ice thickness from 1 to 4 meter thickness. So you can see that there is a lot of little details, and you can study this opening, the leads and the cracks and what's not. This is already used in many publications. One that I want to highlight is one from Xinyu Li, that was published in Nature Climate Change last year, where we actually look in the Arctic in the 1 kilometer resolution and see how the disappearance of sea ice will change the behavior of the currents in the future. So this is December surface in the present day. This this worms inside of the Arctic is actually currents. So it's a snapshot of the currents. So you can see if the sea ice is present, this is present day on the top. You have very kind of not very active currents and the surface and 50 meter depth. But if the ice is gone, you see that there is much more activity going on in the Arctic that has implications for the exchange with the atmosphere as well in the future. All right, so what we are going to do in the Terra-TT project, and why I was talking to you for the last 10 minutes about the FESM ocean model. And so FESM consists of the ocean model itself and also FESIM. So they right now also comprise one big model. What we plan to do is we want to separate FESIM and FESM and couple them back through the external coupler, which is called YAC in our case. So why would you want to do this? Right now, our resolution, as you maybe remember from one of my slides, in the Arctic is about 5 kilometers. And this will allow us to have still, for example, 5 kilometer resolution in the Arctic, in the ocean, but have 1 kilometer resolution in the sea ice. That would be much more interesting for having more details. So same thing can be done for the Baltic Sea. You can have relatively low resolution in the Baltic Sea, but still have quite a high resolution in the sea ice in the Baltic Sea, where you can go I don't know, to 500 meters or maybe even finer, and run them together. We also want to expand it with the ice pack and force it again, put it back into the IFS FESM system. And we potentially will also couple them to different ocean models. Another thing that we are going to develop here and that I will be talking about a little bit is FESM AI emulator. So we'll try to make an AI-based version of our sea ice model. And then the data that will be produced here will be used by sea ice impact models with use of the sea ice observations. Now, a couple of words about sea ice emulator that we started to develop, and basically we have Florent, who did most of the the work, and he has a poster here. So if you have questions, you should ask him more. So the objective is to develop the CI simulator that emulates the behavior of our original FESM model, right? And capture the processes that we actually have there. So the idea here is that we have two forcing variables. It's thermodynamic drivers, 2-meter temperature, and wind, two components of the wind. We have initial conditions, CI's thickness, CI's concentration, and drift. And we want to predict how these initial conditions will change in time when we apply this forcing to them, right? So there is a neural network in between that predicts basically the changes in this parameters. So the data set we did some very low resolution simulations, which has like about 30 kilometers resolution in the Arctic. And as an input, well, I mean, I already said, hours, and we split, of course, the data into training, validation, and test parts. So when the model is trained, we do a rollout. So we first have the initial conditions, we do a prediction, and then we use this prediction in order to generate new initial conditions. So basically add these increments to your initial conditions, you get the next time step, and you move it forward, right? So the only thing that the model see from your initial from the real model that it's trained on is the first time step, right? And you move it forward. In order to train this model is only 30 hours on one GPU, and estimation, like emulation itself, takes 6 minutes for 1 year right now. So it's much faster than the original model. And this is the results. So here on the left-hand side is the target. So what our original model was showing, and on the right-hand side is predicted. So what AI model was giving us. And I mean, we will show here the pictures, like figures for each of the 10-day intervals. Hopefully it will run. No, yeah, now. And you can see that AI model, given the forcing, like temperature and UNV forcing, actually reproduce the data that you have in the original model pretty well. So potentially you can think, like, I mean, it's smoother, yes, and Florent is working on this as well. So we have a version now that it's better in terms of the sharpness of the CIs, but potentially you can actually have replacement of your CIs model with something that is much more lightweight and can be run on the personal computer instead of the HPC. Another example is how this model reproduced the UNV components of the the CIs, and it's actually pretty remarkable because we didn't expect that it will reproduce it so well. But I mean, almost on every single image, if you stop it, I mean, you can see that there is a very good resemblance of one and another. So I'm pretty happy with how it looks like. And if you look at the time series, so here is a mean CI's thickness, CI's extent, and that's an index that measures the difference between your original data and the simulated data and AI generated data. And you can see that you can just run it for 7 years and it's still stable, right? So it doesn't drift anywhere. So it produces the result that pretty much in statistically insignificantly different from the original data. So I mean, we can say that the first version of this emulator is basically ready. The last thing that we'll talk about is the glacier part. So I was asked by our colleagues to talk about this as well. So we will add glaciers also to climate DT models. And it's involved actually a lot of different developments, because right now I mean, it will be implemented in ICON model. ICON model has atmospheric part and ocean part. And in order to implement the glacier, in our case, it will be Elmer ice. You have to have, like, I mean, you have to make the ocean model to understand these cavities, for example, right? So it's something that ICON doesn't have, then they have to be implemented. They also have to implement the energy balance model. The subglacier hydrology, I think, is part of Elmer ice already. And they will be doing this on very high resolution, where Elmer ice will be running also on kilometer resolution. So there are some first examples of ICON fields exchange with Elmer ice. So things are going well. So technically they are working. And the application area will be right now first on the Spitsbergen, and there is some motivation for doing this on the Spitsbergen instead of the Greenland, because, well, I mean, the situation is similar, but we have much more data on Spitsbergen. That's why we will apply it to Spitsbergen. So that's the idea. So that's it. Thank you very much. I think we still have 5 minutes for discussion if you're interested in some more things from me.
Thank you, Nikolai. Questions from the audience? Jari was faster, so.
Yeah. I hope that I didn't steal the question of Till. But, you know, I think that of course, these simulations, what you showed are really amazing and really great and useful. But one of the things what the destination Terra DT have to really provide for the users uncertainties. And when we are talking about the climate change, that there's like several uncertainties. If you think about the climate variability, natural variability, then it comes from it's a system itself. What is the nonlinear dynamics and on this coupled system? Then it's about the initial conditions, and then it's about the CO2 emissions. Mm-hmm. And then if it's like old school papers say that if you look up at the next 20 years, 30 years, the emission doesn't matter. So the emissions are pretty stable, and we understand the impact of emissions. So it's very much of the internal variability, both in the model and both in nature. And for you, of course, it's about the initial conditions, how you initialize your ocean model. And then it's about the natural, the nonlinear system itself. And for that, you need to have the data ensembles. So how you can, what is your answer for the people which are using your data? Because you are not, because of the computing resources, you cannot produce the huge ensembles. You cannot produce 1,000-year simulations to get the stable initial conditions. So what is your advice for us which are using the data? What kind of error bars? When we are talking about using the climate DT data, for example, for the next 20 years and so on, what is the uncertainty? What is the?
Well, I mean, that's certainly something that we take very seriously. And about the initial conditions, I can tell you that, well, I mean, we right now have only 5-year spin up of the ocean, because the ocean is also pretty expensive, and we just move with that. I mean, we try to increase it, but and there are some ideas how to do it, and some of them involve also AI, right? So that we actually can run low resolution ocean and try to spin it up in the low resolution and then kind of interpolate it and use these things as initial conditions for our spin up. So regarding the ensemble generation, it's a little bit more difficult, of course, with the amount of resources that we require. But I mean, that becomes very critical. And one of the approaches is that we're discussing right now is maybe to run a little bit lower resolution, like 10 kilometer resolution instead of 5. but run the ensembles. And the BAC is already producing 10-kilometer ensemble members. And it's not going to be huge ensembles, but I think like we can afford something like 3 ensemble members for each of the models. And also you can see that, okay, our models are not entirely independent, especially if you talk about IFS, FESM, IFS NEMO, but it's still 3 different models. So like multimodal ensemble means something that you can work with as well. And the last thing that I would mention is that in terms of ensemble uncertainty, one of the ideas is to generate emulators of the climate models from our models and run the ensemble members with these emulators then. And then we can generate like thousands of ensemble members if we want. Still, it's still a research question how useful it is, how much it represents the like real ensemble if you would generate it with real models. This is something that we can test on the low resolution results. But I mean, my hope is to have this uncertainty estimates from the AI generated like emulators that are trained on the data from our models. So that would be my answer.
Thank you. Till.
Thanks, and thanks for the presentation. A question on the AI part. So you say you are only using the surface temperatures and the winds and the state of the ice. Does this mean that the ocean is to be disregarded? Or have you tested that?
Well, I mean, we just talk about it with Florent, and he will give you much more detailed information on that. But and if you use sea ice, like ocean temperature, the sea ice information is so much imprinted in the ocean temperature that it becomes like too strong of a constraint, right? From my understanding. So that's why we decide not to use the ocean temperature, because then you kind of like, I mean, if you're going to couple it in the future, you have to get this information somehow from the ocean model itself, right? And you don't want to be dependent on this information. I hope I didn't mess it up wrong. So maybe you can talk to Chile afterwards, but that was the motivation. Yeah.
Okay, thank you. Any more questions from the audience? If not, then thank you, Nikolai. Nikolai will be here during today and tomorrow, so you can torture him during coffee breaks and lunch. So, but now, lunch. Yeah. Now it's time for lunch. The lunch will be served somewhere here, and we continue at 1 o'clock. So,
I don't believe it. Or, yeah. They said that it's always on. Welcome back.
and let's start the next session. In this session, we will take a closer look at the concrete applications that we have produced in these two projects, starting with the sea ice impact model of Terra DT, and then continuing with the 6 use cases of NOCOS DT presented by the developers from each of our partners. So welcome, Ilya, you're the first.
Hello, my name is Ilya, and on behalf of our small Baltic team, I would like to give you a short overview. What have we done in NOCOS DT project, and what's the upcoming challenges for Terra DT? So my part is to talk about rich ice application today. So possibly there are much more experienced scientists among us who don't have to be introduced what is rich ice, but here is a short overview that just very general overview what it is. So in short, this is the perhaps most hazardous ice type on the ice field, since you can see it consists of quite small rich sail, and underneath it's a huge rich keel, almost like iceberg in the field of ice where you don't have one big ice mountain heading toward you. So and in Baltic Sea, this kind of ice feature or ice phenomenon is quite frequent, as it forms during the strong wind events, when really strong winds pressurize ice fields, and therefore ice starts to deform and pile on top of each other. So what are the typical dimensions? Approximately rich sail, the visible part of this rich ice, is up to, I don't know, 2 meters when it's offshore. When it lands, it might reach up to 10. I've been myself 10-meter high. This landed rich pile, so quite a big chunk of ice mountain. But what is more dangerous is what's beneath that. There's a consolidated ice layer which act as just very thick and very dense layer. It's not just a pile of small ice flows. So it's comprised big risk to whatever is moving on the sea. So winter navigation is very much affected by that. And recently, when we have this offshore wind farm developments, the also first question is that does the rich ice occurs in that region or not? But one even slightly less studied, I think, risk is what this rich ice keel even does to the under the surface. It as it reach sometimes even to 20 meters in Bothnia Sea, it can easily scrap the ice bottom, and whatever is installed there also is under really great risk of being broken. So our goal was to quantify it or evaluate from models, and this was quite a challenge, because in typical ocean model outputs products, only in very few ice models is a clearly labeled rich ice type. but you often have to just look at some ice class that looks like, that has characteristics for the reached ice. So typically it's just the thickest ice class from the ice model. And if you're lucky, it exists somewhere in the product. If you are modeler yourself, then yes, you have it somewhere in the background. But typically, you might not have. The most direct proxy is the process itself that can be tracked sometimes in the model when ridging as a process is involved there. And there we have also tested to just count the amount, the water that is frozen due to this deformation. Very complicated, very unsure. But in my opinion, the most accurate thing to actually track the ridging. But what we have is typically only sea ice concentration from 0 to 1, and ice thickness from 0 to infinity. So that's our two proxies for reached ice. And from the models, yeah, I've tracked it in the way that I've tracked it, the voids, the porosity, the voids that occur during the ridging, what's left into reached ice due to this deformation. So principle, very narrow concentration area and relatively large ice thickness in the two parameters that can characterize this kind of things. This is quite uncertain proxy, but that's what we have to deal and work with. And yeah, our NOCOS goal was to evaluate the climate DT data regarding that. So here's at least three bullets that what we learned from that. So first, that's resolution is quite sufficient already. Indeed, promised kilometer scale, slightly more than 1 kilometer, but already quite comparable with our local ice models and ice products. Yes, as Jari before said, that there are biases, they have to be addressed, and that was the main concern during the project, that how to deal that, what's the useful information, can we extract the useful information from that. So I would say that yes, they are wrong, but it's our job to address these uncertainties, and so that Nikolai could fix them. So but the biggest experience and new innovation was actually testing out this destination Earth's, I would say, data ecosystem, how this data is really transferred to this cloud. I will not say data lake, but cloud, and how I will access to cloud, log into cloud, and really work outside of my computer in some service environment. So for me as a data scientist, that was a quite interesting journey. And thank God, this is errata exists there. And I have added also here one line that you have to keep into, you have to remember that this is a product. Therefore, a lot of money have been put there for a service desk. As I yesterday learned, there are service queue for users. If users have a problem, then they have a paid service that this concern will be fixed or addressed. And this is the other dimension of that new data service, that it is not just sending to scientists, hey, your publication validation is well, plausible, questionable. Some service queue has to address your concerns, and that's interesting. New way for accessing and using the data. So I would say that this is the best thing that we reached, which shows regarding the reached ice from Climate DT. On the left hand, you can see this probability in days, how this reached ice looks in the Copernicus marine reanalysis. Yes, also model, also biases. But this is our best knowledge of past historical this dynamical model ice climate. The blue one line corresponds to packed ice presence, which is above 0.8 concentration. And on the right hand, two simulations of climate. One is the historical, that should look like exactly like this realistic ice climate. And on the most right panel, this is a future 30 to 39 ice climate. As you can see, yes, there are biases on the historical two plots. More or less the extent of packed ice and reached ice are more or less similar. It model overestimates with this proxy, I must again underline in the most northern part of the basins. But if you look at the change, now this is the thing that where we can assess or say something about climate change. Then hey, first thing, ice is not completely lost in the Baltic Sea in the next 20 years. But it indeed shows a great reduction in the reached ice probabilities. But why I plot this blue line here is that this is still the ice which has potential to be heavily deformed. This is a packed ice. Okay, this has not enough, perhaps, the thickness to create this big reached ice piles, but it has potential to cause damage to offshore constructions. This is IFS Nemo, because icon is a little bit unusable. FESM has 2-degree scenarios, not for climates. But I have for that also a case study tomorrow. So, but coming back to pack ice, here is a small case study that we did for the Utilitas wind farm development, and where we had exactly that. Okay, sorry, Utilitas had this concern, but what happens with the packed ice after it has been damaged by the wind farms? And for that, we first implemented simple parameterization to our hydrodynamical model coupled with ice, added some simple stress parameterization to ice field, which already, as you can see on the lower plot, already distorted a lot of big part of Gulf of Riga ice. It didn't increase the ice in total volume, but it changed the fraction or new leads that had happened. So geometry of ice was affected. Yes, work in progress. My gut feeling is that this stress is a little bit too high as it's constant, but there are some new papers that show how this stress should be reduced. So I must again underscore that this is perhaps the worst case scenario when really ice is nailed to the bottom and has hindered it to move. And really to track now, where does this deformed ice go? We implemented a simple post-processing Lagrangian model, which for all the pylon coordinates injects some kind of virtual particle that expresses the deformed ice and let it just float around how in the ice field movement, ice drift movement. So this really showed that this deformed ice that's originated from wind farm can easily reach to whole basin in principle, especially in the severe winter of 2011 when we had a lot of easterlies, subsequent westerly winds. The ice was in constant movement almost in that region. So yeah, more or less this kind of small Lagrangian analysis also performed on the climate DT data. But okay, resolution was not perhaps the best, but still 5 kilometers and daily resolution could show some directions where these particles would end up, which are damaged by this. Now that there are two wind farm development areas, and that sort of integrates both how ice moves and where does this packed ice develop in the past climate and future climate. And so yeah, with this I think my time is more or less over for that. So if you have more questions or concerns, let me know.
Thank you. Thanks a lot, Ilya, for the talk. It's nice to see that our data actually used by somebody. But I mean, you asked for some additional variables, right? That is not available for you, and I'm afraid that I guess there is not much hope in having much more variable to be outputted from the climate, from the digital twins. But would that help you if there will be algorithms or applications that would compute these additional variables post-mortem, let's say, using the same algorithms that are used in our sea ice models afterwards? I mean, for example, deformation, right? So we are not going to output the deformation, but if we can use UV and sea ice, other sea ice properties to compute deformation and also provide it as an additional variable for you, or inside of your application, you can basically have these algorithms to compute this information. Would it help you?
I would say no. I can myself also calculate divergence or estimate that, okay, wind farms deform ice here, right? Wind farms don't deform ice anywhere else. But you cannot track, if you give me the process or this rate how this ice deformed or reached or whatever, this does not tell me where does it end up, the direction. The ice movement will be, okay, you have to do all this tracking also post-process then. That's, I would say if you would just have click to switch on ridging in your dynamical model would be much more easier to track it. But at least if you have that algorithm processes as a proxy, they are better than nothing, I say. So yes and no.
I mean, so far you can sort of survive with what we provide. So basically thickness concentration and UNV. So it's not like, okay, good.
And already there, we can develop use to them, I would say. So yeah.
Thank you, and thanks for the talk. I have a question regarding the bridging charts on the whole Baltic Sea. I realized that you also had deformation with your proxy. Your proxy gives deformation also close to the coast, where there's a, in some places at least, quite a wide fast ice regime. Is this something you've considered? In the beginning, you talked about categorization, about the different ice types, and their fast ice is definitely one. Yeah, they in the animation you have it developed quite nicely there. But on the next slide, there's the proxy gives ridging ice quite far into the fast ice regime, and that is my question. Is this something you have been validated to ice chart information, or?
In principle, this is what we can validate it from the ice charts, as it's the models which we are working with. These are our local Estonian forecast model and Copernicus ice model. Here I show the outputs of Climate DT, what we have to rely that they are thickness and concentrations. And I don't know if it's fast ice there or what ice type there. I just can proxy from these concentration and thicknesses that it's a rich type, but not exactly rich ice. So for this, validation has to come, but it's a matter of validating this historical run simulation. What here shown is what happened in the future slides. And also you can see that already here I noticed that that perhaps in some regions we have also already in Climate DT quite well shielded coastline that prohibit this deformed ice ending up near the shore, while in the future we don't have this shielding landfast ice. It's our coastal areas are more impacted. So this kind of, I would say, virtual information can be extracted from Climate DT. The realism is something that has to also follow to address these uncertainties.
Thank you.
Yep, now it's on. Okay, thank you. You can ask more questions during the breaks or then in the social section tonight. Let's move on to next one. It's Xingfang with the ship navigation risk indicator.
Hey, my name is Xingfang. I'm from Finnish Meteorological Institute. I'm going to give an introduction on the ship navigation risk indicator use case on behalf of NOCOS DT project. So the ship navigability in ice-covered seas depends on ice concentration, thickness, ridge ice fraction, ice drifting speed, and compression. But of course, in this use case, we only focus on mainly ice concentration and thickness. And of course, essentially the vessel's ice class. IMO has introduced a risk index outcome RIO method to provide ship-specific guidelines for safe navigation in ice-infested waters. And calculating this risk index outcome requires accurate and high-resolution sea ice information. In this task, we developed a method to calculate navigation risk indicator RIO from the model data. In the first phase, when the destination Earth data is not available yet, we use the existing models like Copernicus, ECMWF, and DMI high-concise sea ice forecasting data to develop this indicator. And in the second phase, when the destination Earth data is available, we implement the developed method on the Climate DT environment, where the input data is global and high-resolution climate digital twin. The statistic of RIO helps us to estimate the efficiency of the newly designed vessels, shipping routes and harbors, and provide guidelines for safe and cost-effective shipping. So here's an example of the Rio distribution in the Arctic. On the left-hand side, it is the IFS NEMO model, and on the right-hand side is the ICON model. They are both the average April Rio between 2030 and 2039. So how do we calculate Rio? First, we need to have the sea ice concentration parameter. Then we need to have this risk index value. How do we get the risk index value is first we need to have, okay, what kind of ice type is it according to the polarized ice type? Then we need to have the assigned ship class. Here we assign the ship class to be PC5, and then of course, our method developed that we want to have sea ice thickness, salinity, and age to accurately map what polarized ice type we have. But unfortunately, in destination Earth data, we don't have ice age or salinity parameters yet. So we just vaguely map the polarized ice type based on the ice thickness. So as we have the ice type and we have this PC5, we got the risk index value, and we plug it back and multiply with the concentration, then we get the real value. So there's a predefined color code based on IMO. So if the real is greater than 0, it is marked with a green color and it indicates safe navigation. If it is between -10 and 0, it is marked with yellow and it indicates the elevated risk level. And if it is less than -10, then it is our so-called no-go zone, and it is marked with the red color. Especially for this no-go zone, we have examined that the sea ice concentration behind it is nearly 100%. So this is this is in 10, so it is 1/10. And then we know that it is PC5, so the real value is pretty much dependent on sea ice thickness. That's why we also plotted the ice thickness map average for April within these 10 years. On the left is IFS NEMO, and on the right side is ICON. We can see that the IFS NEMO simulates an excess amount of sea ice, but in ICON model, it simulates a very little amount of ice. Therefore, the navigation risk simulated by the IFS NEMO model is there's way much more risk than simulated by ICON model, despite they are exactly in the same time period and for same ship class, and they are both in April. Then we did statistic on transpolar Rio. Before the destination Earth data is available, we calculated transpolar Rio based on our 3 selected models. They are DMR Hycom models, Copernicus model, and ECMWF subseasonal to seasonal forecast models. So for the transpolar route and for a certain time period, we selected a mosaic expedition period. So this transpolar route piles up and it becomes a 2D profile. The x-axis is the transpolar route. We just rotate it like this. So it is from 70° north to 90° north and back on the other side of 180° longitude, back to 70° north. So this is the x-axis, and the y-axis is the time period of concern. We can see that among models and between the models and ice chart, I forgot to mention that we validated our transpolar Rio profile against the ice chart. And for ice chart, we use the same method. So we can see that there's a clear difference among modeled transpolar Rio profile. And there's also very much difference between the models and the ice charts. And this is especially shown in PC5. So for my paper or my future analysis and previous analysis, I mainly focus on this PC5. And then in the second phase, after the destination Earth modeling data is available. I want to repeat the same thing that I did for these 3 models. So I validated the transpolar real from the ICON model. This is ICON model, and this is ice chart. We can see that the ICON model is like severely underestimating the navigation risk. We wanted to do the validation for IFS NEMO model also, but there's no time overlap between the ice chart and the IFS NEMO model. But it is possible in the future. So that's all for my use case. Thank you.
Let's have the questions during the break so that we can finish all of these use cases in time. So thank you. Next, we have Landfast Ice with Andrea. Please stand close to the mic.
Something like this? Yes. Yeah, so I will continue with Landfast Ice, where we have been working at DMI, as you can see. Landfast Ice, I guess many people here know it because if you live close to the Baltic Sea, you have it kind of in front of your door. It's the immobile sea ice that is forming often, close to the coast, close to islands, with a fully ice cover, as you can see in the picture to the left. This is an example from Greenland, where the full fjord is ice covered in wintertime with landfast ice. So that's the ice we are interested in here. It's important for the climate system, but as you can see, also for people living in Greenland, they are using the ice to travel on with dog sledges for hunting, for fishing. This is us doing fieldwork, but basically the same principle. So how, as you see, it's important for the people living there. How do we know about fast ice? One possibility is to use ice charts. So people actually sitting in the office looking at satellite images and drawing these maps, where in this case, all the gray areas are landfast ice detected by different methods. I show examples here for March. I picked just 2 random maps for 2015 and 2020, where you see, the ice, fast ice is different from year to year, from week to week. So to get an overview of how usually fast ice is distributed, what I did is I just picked all ice charts I could find for 10 years, 2010 to 2019, and put them together. And then I can kind of calculate where there usually is fast ice. Yellow means there's always fast ice in March in these ice charts. Blue means there is no fast ice. So as expected, the fast ice is around the coast, in the fjords, sometimes a bit out here. So yeah, that's the current state, so to say. Now we ask the question, does it change in future? This image is, of course, not from the future, as you can see. It's just in autumn when the ice is still thin. But who knows? How does it look in future? The problem is that landfast ice is a coastal feature, so we would need very high resolution in the models to show it. State-of-the-art climate models. So we were asking, what can Climate DT do? Because it's a high-resolution model. So let's try it. How do we get fast ice from a model? The model doesn't really give you a variable saying this is fast ice, but it gives you variables like ice concentration, the ice drift, thickness. So we need to calculate it from that. We get daily mean values, so that's what we use. Our criterion we defined for when ice is fast ice, we require that the ice drift speed is below a certain threshold. We require that the ice concentration is high. And we say this needs to be valid for a certain amount of days. The reasoning is that we say fast ice is immobile, so that's why it should be slow. It's a fully ice-covered area. That's why we have high ice concentration. And of course, it could be that the ice is just not moving because there's no wind or whatever. So we say it should not move for a while, so we can define it as fast ice. So let's try it. We take the icon model and derive fast ice from that. The map works like as you saw before, like the more yellow, the more usual there is fast ice. And on the left-hand side, we have the present day climate, so to say, an average of the last 10 years. And on the right-hand side is the future from the icon simulations. Yeah, what you can see, we have the fast ice around the coasts. I have a zoom here to Ingelfield Fjord, which is where the pictures were from. So just to get a reference. It shows like, okay, there is a bit less fast ice maybe in future. But in general, do you still remember the map I showed from the ice charts? That was, was way more fast ice even in the current period. So that was maybe our main conclusion for now, that yeah, the icon model at least cannot really reproduce the fast ice. So to summarize, in our work package, so to say, or like use case, we have made this software for Python code to derive land fast ice from the climate DT models. And what we saw is climate DT is quite good because it has the high resolution. You can actually resolve the fjord. But we also see that the icon model overestimates the ice drift, and that's why it doesn't show enough fast ice. You can see the ice drift speed here. So it seems like the icon model doesn't really have taken into account maybe parameterizations for the land fast ice, which is something that could be improved, I guess, because people living there and people living in the Baltic Sea would have the same, maybe would be interested in how fast ice looks in future. Yes, thank you.
Thank you. Next, we have marginal ice zone and Kekwang.
Oh, sorry. My name is Kekwang, working in Met Norway. I'm talking this marginal ice zone a bit different from the previous talks, I think. Mostly, I think we do this like parallel ways. One is to try to, I think, to improve, to investigate method how to improve the modeling of this marginal ice zone. And the second is to show how this developer this software to show the climate application to the climate DT applications. So basically, I think in the last 3 years, we have made the main effort in to try to improve short-term forecast marginal ice zones, and also for sub-seasonal. This is for sub-seasonal to seasonal sea ice forecast together with the marginal ice zones. I think we have found some method by include model resolutions and data simulations for short-term to sub-seasonal and seasonal forecast for the marginal ice zones. And also, I think, to put some effort to define and to evaluate and then to construct an overall structure for the defining and evaluation of the marginal ice zones for some of this like some of this climate DT or other model system forecast applications. So some of the very basic, I think, some of these marginal ice zones, we usually call these marginal ice zones is some of this like a bit of this open sea ice area between the open water and a very dense sea ice. So we here have traditional marginal ice zone and a dynamic marginal ice zone. So traditional marginal ice zone is basically, I think, only looking at the ice concentration, which is between like 10% or 15% to 80%. This is quite arbitrary, I think. It's personally, I think it's 0.85 will be, I think, more reasonable because this is separated between very close ice to the very close ice. But from the historical, I think we have a lot of sea ice charting, just defined by this. So this is followed in our studies. And for the dynamic marginal ice zones, here actually it's looking how the waves affect as a sea ice. So we have also considered making some of this model simulation from our other people's model simulations to parameterize how to taking account of the effect of the waves based on the ice thickness. So then for thin ice, we can also see some of the as a dynamic marginal ice zones. This means some of the thin ice will heavily affected by the sea by the waves. So if we consider this is answer 2, traditional band marginal ice zone, and this usually it's ice chart is regarded as the best observation. And compare with this, then we see some of the very thin ice actually in answer 2 is often, I think, missed if we compare with a lot of different ice observations. And this is some work just to combine these two data sets because like answer 2 data, we have some of the fun features, and this is ice chart. Usually such features missed. So it's some of these studies try to I think improve how to define and calculate the marginal ice zones. And then this is how to evaluate marginal ice zone simulations. So we introduce this integrated marginal ice zone error in two papers. Then it's looking for each grid, model grid. This is like a forecast, and this is a truth. So this is if it's marginal ice zone, then C is 1. If it's not, then it's 0. So it's basically is very close to the definition of the integrated ice edge error. Then we compare, apply this evaluation metrics to different models, observation and model systems like AMSA2, SSMIS, NEMO, TOBAS, NEXIM, and our model system, it's pan-Arctic high-resolution models. So we compare how data simulation affect the overall like 1.5 year simulations, and see really high resolution helps, and also the data simulation helps a lot. And this is another, it's quite regional in the balance, it's in balance area. So then we see it's really with better observations in the simulation, in a simulation. So then it helps the overall forecast and also analysis of the marginal zones. Some of the quite preliminary quality in testing of the climate DT marginal zones. Yeah, basically I think compare with rigid ice and also like risk shipping risk index. Then marginal ice is quite, I think, it's sensitive because it's at the ice edge, and the change of the ice extent can change quite a lot of the overall sea ice area. Then if we compare with this ICOM winter marginal ice zone together with IF NEMO winter ice zone with National Ice Center marginal ice zones, then really I think it's overestimate some bit, and this one is closer. And also we looking the summertime, and both of this ICOM and NEMO has like overestimate of these marginal ice zones. Yeah, I think this is what we have done in the project. Okay.
Then we have marine spatial planning, and Lars.
Yeah, thank you. So I'm going to present some work done mainly by Lynn Karlstedt in our group, who is on maternity leave now. We have worked with this how to get data that is usable for marine spatial planning. And to say something about what marine spatial planning is, so the purpose of marine spatial planning is mainly to contribute to a long-term sustainable development of the marine space, where you kind of integrate both the economic, social, and environmental objectives into this. So these plans, they should contribute to good environmental status in the marine environment. They should contribute to giving marine resources that can be used sustainably, also so that we can have this blue economy developing there. And then there needs to be coexistence between different users, so that we, in an optimal way, can use the ocean space in a good way and still have a good sustainable environment out there. And the source of this is the Swedish Agency for Marine and Water Management in Sweden that are responsible for this planning in Sweden. They also state that we should use an ecosystem-based approach to do work with this, although it's quite unclear what that is. And then we also know that climate change is really important for the marine environment, for all of these factors, both the ecology, but also the uses and the possibilities of coexistence. And so we've studied with focus on the ecology. We've focused on trying to determine the impact of climate change on the ecosystems. And the figure to the right there shows for 2 climate scenarios focused on Swedish waters, how much the pressure increases when you introduce climate change onto the other pressures that are already present out there. And what we see is that, especially up in the Gulf of Bothnia, there's a huge increase in pressure due to climate change. It's less in other regions where the pressure is larger today, but up there the pressure is quite small today. So climate change is really causing a large increasing pressure there. But then climate change is often not really included in many of these spatial plans when they're developed. So it's important to get that in there. To produce these maps, there was some expert input, expert assessment into different ecosystem components to see how does different climate change factors stress these different ecosystem components. And we focused on surface and bottom temperature, surface and bottom salinity, and then for sea ice as well. And that's the figure, the columns to the right out there. And that was for the 3 main basins, the West Coast, the Baltic proper, and for the Gulf of Bothnia. What you see for sea ice is that it's green mostly all over the place. But for example, seals, it's important if there's ice or not. And also for some fish, it's important that for fish spawning and fish, river mouth fish, it's important to have sea ice. So if the sea ice is decreasing, that has an influence on the ecosystem. And then you also see that for many of in the other regions, for salinity and temperature, there's a lot of ecosystem components that are really largely influenced by changes due to salinity and temperature changes. So our focus here was to kind of produce scripts so we could extract those kinds of data from the climate DT. And these plots that I show here is not from climate DT, they're from our own climate models, but they kind of show what kind of plots we can produce from those data that comes out from climate DT. And which are, for example, this one showed was one of the relevant parameters, how many days you have ice cover in different regions. And you see this is really decreasing in the future. So we developed Python tools to do this. We have a kind of a Python framework working in X-ray and Dask called Doris to work with these data. And then some other processing toolbox as well. And we can produce this kind of plots. And also the important thing is there also that, like Jari mentioned, it's important if that you have more than one ensemble member, so you can also look into the uncertainty of your future CI states. And then we also, when we looked into the data, we didn't do a thorough analysis of the climate DT output, but both in those data and our own data, we find there's biases in all of the parameters in the historical climate. So that's something we need to deal with. So we also started looking into bias correction, because this may be quite important if you look into details of different habitats. If the salinity is 3 or 5 PSU, it makes quite a big difference. So you need to make some kind of corrections for that in the historical climate, so to get something meaningful for the spatial planning. So we started developing that, and Lynn managed to do that for temperature, but she didn't really get it finished with the sea ice. Sea ice is a little bit more complicated, but because you have this finite 0 cutoff, and then you have so it's a different distribution. So when you do this bias correction, you need to look at the whole distribution and see how that changes, how that is represented in the model compared to reality, and correct for that. So that's basically what we did in NOCOS. Thank you. You can ask me afterwards if you have questions.
Thank you. And finally, we have Jan and discrete element model.
So I could stand here and tell you about my model, but instead I thought I'd show you some animation so you will get an idea. I hope this plays now. So, okay, that's nothing. Does it play, or should I click one more? One more time. No, it doesn't play. Yeah, doesn't play. It plays there on the. Okay, now it's playing. Yeah. Okay, so this is 2 wind power pylons here, like 10 meters in diameter, and outside this now to the left, I am compressing the ice to make a compression ridge. So there is some dynamics going on, but I'm not still allowing this. But in 50 seconds in, the ice will start moving. It's pressed with wind and currents with quite a high force. So this is the first video. I have another one where there is a shear ridges formation in a larger zone to the left also. So it should start moving at 50 seconds about. So it will start. Okay, there it goes. So here is no. Why did it vanish? Okay, just leave it as it is. So here is it's a little bit bad, the resolution now, but this is the compression ridge coming in. So this is about like 6-7 meters thick and like 10 meters wide. And you see the force is now so high, so it goes through this level ice. The wind power pylons is going like icebreakers through them. And this is not consolidated ice in this compression ridge. I didn't use any consolidation here in these simulations. So now you see the ridge will soon hit the compression ridge. So this is just really a ridge of ice rubble, so it's just a pile. But as you can see now when it hits the it hits the ridge, the ice to the left of it will basically stop moving, and the ridge will start to, you see the disintegration has started already, because this is kind of breaking it now, so it's stopping, and all this ice here is stopping, and the ridge begins to disintegrate, and all the ice to the right side of the things that has stopped will begin to disintegrate. So this is really a demonstration on how you can make these kind of models, see what these kind of pylons, how they can really break up the ice quite considerably. You will see here now the ridge is completely disintegrating, except in this region here it will stay, but eventually it will start moving around. So this is with the diameter here now is the pylons is 10 meters, and the resolution of the ice is 25 centimeters. So that is also the thickness of the ice, and the temporal resolution is 10 to minus 4 seconds. So 1 in 10,000 seconds is a time step. So 10,000 time steps for 1 second. So it's quite a high resolution. But this is what you have to do, because the speed of sound in ice is so high, and have to have at least 10 time steps for the speed of sound going past 25 centimeters. So that's what I need so high. It's about 1,000 meters per second. So you could actually put the sound on this, because I simulate the sound, so we could hear the cracking and banging of the ice, because that's also in the simulation. All the dynamics is there.
You have this wind stress.
Yeah, I just put stress on all the particles, and that, of course, you can translate this to wind and current stress. But I don't simulate the wind. There is no hydrodynamics or air dynamics or anything. It's just the ice dynamics. Only the water that produces drag. So now disintegrating. Lots of ice pieces flowing around. So this is in this picture, in this simulation, I had about 100 million particles. So in this show, maybe 10 million or so. So it's just a small fraction of the whole simulation. I can do up to 1 billion particles reasonably. So if I do a meter simulation, then I can do quite large areas also, but not with this high resolution. So there should be another one. This is. This is the other one, yes. So this is a bigger simulation. So, and I had a huge, to the left here, I had a huge area where I made a network of shear ridges. So it's a lot of shear deformations. And now you can see the dynamics changes completely. And you will see, if you look carefully, you will see that this is rafting. You see here, this is going under. And its other place also here, it starts moving under. So this is the very significant change in the dynamics if you go from compression ridges to shear ridges. And this is now the simulation. So the ice will meet land far to the right side there. So, but you can see these pylons, they act as kind of, there is not much, this ice is not moving at all.
Trying to use this so that people can hear it from home, so that you can point and
yeah, so this ice is not moving at all here. It's just mainly rafting. There is no water there, so you can see that the red, it's about 5 meter deep water in this. And you can still see there on the right edge, there is the ice is still it's not moving, but eventually it will break up so much that it will all be pushed out. Okay, that's it. Thank you.
Thank you. And now it's time for our first panel discussion with the title Infrastructure in the Cryosphere. And we are presently 15 minutes behind the schedule, so feel free to go 15 minutes over time. We have some extra time in the afternoon, so the break can start a bit later if you want to. So Rivo, please take the floor.
Okay, we have the first panel discussion. So the topic is infrastructure in cryosphere. So building stuff in ice-covered seas. Why we are talking about it is because currently we are in Tallinn. It's like 10 times 10 kilometers, couple of model grids, 400,000 people. If we go offshore, then we have a lot of model grids and no people and some infrastructure. So I would say it's safe to say that our activities are moving offshore. So as Lars, as one of the panelists, please come here. Already said, marine spatial planning is influencing us. So then we have in the panel also Natasha Ferry-Pettersen from Vattenfall, one of the largest offshore wind energy developers. She will be joining us online. Natasha, can you hear us?
Yes, I do. Can you hear me?
Welcome to Tallinn. Welcome to Tallinn.
Thank you. Greetings from Denmark.
Thank you. And then we have a professor from Baltic, Mihkel Kõrgesaar, whose expertise is naval architecture, which also includes some aspects of sea ice. Put your arm around. So we have three distinguished guests, and we're going to talk about infrastructure in sea ice. First, I would like to take an introductory round. So could you please explain a bit what is your background, how you're related to sea ice, digital twins, or offshore constructions, let's say, starting here, Lars.
Do you hear me? Yeah, it's on. Good. Yeah. So I'm working at SMSI, which is similar to what we heard earlier today from Tallinn here. So we're producing ice information in the same way, more or less. But yeah, so that, I guess, for ice, that's what we are doing. Then we are also looking into, we have had some projects to look into environmental effects of wind farms, for example. And now we are part of your project that you're leading also to make climate, like make digital twins about looking into the influence of offshore wind farms in the marine environment. Yep, thank you.
So then it's good to continue with Natasha. So Lars mentioned one project already.
Yes, so yeah, I'm Natasha. I'm a mid-ocean engineer in the business area offshore wind in Vattenfall. So I have a background. I'm an oceanographer from background. 10 years now of experience in offshore wind. I don't have that much experience in sea ice, but Vattenfall is looking at some projects and sites in the Baltic Sea and in ice-covered waters. So that's why we are here today. Vattenfall is also involved in research projects where we try to get the latest knowledge of digital twins, climate data. So that's why we're very much interested in also collaboration with institutions like yours.
Okay, thank you. And Mihkel, what's your relation to sea ice and stuff in the sea?
Yes, hello, my name is Mihkel Kõrgesaar. I'm an associate professor in naval architecture and marine structures in Baltic. And I think my first introduction to, let's say, ships in ice was in 2016 when we started to build some Horizon project related to that. And at the moment, we are also building a project together with DTU, NTNU, Aalto, Chalmers, and Gothenburg to hire a bunch of doctoral students to work on, let's say, safety of ships in ice. So my perspective has been, and I think at the moment is that how do we can safely operate those structures in ice? You're trying to build different numerical models and also maybe going towards digital twins a bit. So that is my association.
Thank you. Now coming back to Lars's presentation. So what is your general opinion? Can the digital twins support marine spatial planning, and how? Is the sea ice information sufficiently good at the moment in digital twins, Climate DT, or it has room for improvement?
That was a leading question. Yeah, of course, there's room for improvement. And I think in this project, we expected to have the data before. So we didn't really have time to look into the details of how good they were. But so I think there's a lot of possibilities for improvements. And also to have, as I think it's important, as I said before, and as Jari also mentioned, that we have, like both you have something that looks good in the historical period, but you also need like more than one or two, maybe even more than three ensemble members to work with. If you want to say something about not only how it will change in the future, but also something about the uncertainties of these, both of ice, but also other parameters. So I think it's a big investment, and I think there's still some way to go.
Okay. Main message is that you need ensembles and uncertainty estimates, basically.
Yeah, we need that as well. Sure. I mean, having just one path into the future with one model would not tell me that much.
I guess in a way, these are the different scenarios, are the what if scenarios. So what will happen if something happens with the climate in one or the other direction?
Yeah, so it's both. So of course you can look into different scenarios for climate, for carbon dioxide release, but also even for each of those you would need to have several ensemble members with different initial conditions, different models, different parameters to see what. And of course I mean you always have to have a compromise there, but at least you need some models to do that with.
Yeah, now I understand your point. I'm a scientist as well, so the more the data, the better. So, but what about the practical point of view, Natasha? Could you, let's say, walk us through what kind of data you are using in your development projects or pre-studies for selecting the sites, and how you handle the data?
Yeah, sure. So yeah, maybe I didn't introduce Vattenfall, but Vattenfall is one of Europe's largest producers and retailers of electricity and heat. So, but we are based only in Europe, and we have offshore wind farms in the German waters, in the Dutch waters, in the UK waters, Danish waters, and looking at Finland right now. So in terms of data, yes, we have to support in the mid-ocean team. So mid-ocean stands for those who don't know, meteorological and oceanographic. So we are supporting through all the phases of an offshore wind farm, from the site screening, checking feasibility, towards design, and then operation, installation, maintenance, until sometimes lifetime extension as well, and decommissioning. So in terms of data, we're looking at everything, and I will mention the basic waves, currents, wind, water levels. So it's very comprehensive because they're essential for foundation design, for example, cable routing and the marine operations. In terms of sea ice, we are looking, I saw a lot of presentation about it today, but the sea ice, the ice thickness, the coverage, its velocity, the dynamics of it as well. So the interaction between the structures and in the ice. We are very new at it, so most of the time we have consultants or universities helping out on this topic. In terms of data as well, we're looking at data inside the water. So water temperature, water salinity, turbidity. Most of this data is used for environmental impact assessments. We have to model ecological interactions as well, and we have to monitor those variables. A last set of data I could think about is birds, bats, and mammals. We have to survey the habitats because this is again included in those impact environmental assessment. But we have to make sure we are protecting the biodiversity because we are introducing new elements in the offshore waters. And the last thing are the climate data, where we are trying to come into research or European projects to get more idea or more knowledge about what is gonna happen, because we think it has an impact, for example, on the wind speed, on the water levels, on water temperature. So we are looking at what is the impact, because those farms, they stay at least 30 years in the water. So we need to know how well are we designing.
I have one additional question. You mentioned that you use the data for ecological purposes, for, let's say, what is required by environmental impact assessment, and then for structural design. Can you say like how much of the data or budget is for one or the other, or is it the impolite question from my side?
Basically, we try, depending on the phase of the project, we will go for public data first, because when we develop the sites, we don't have that much budget. So we were going for public data, Copernicus, everyone knows about it. And there's a lot of in-situ measurement as well available for the North Sea. So we're lucky with this. When it comes to design, we start to carry out mid-ocean measurement campaigns. So we are going offshore and measuring our parameters for 1 to 2 years. Sometimes also in the development phase, where we need to know about the site. So there we start to budget, and it's millions, basically, that go into such campaigns. For the design, additionally, we go for a consultant that will give us a very high resolution modeling study to have a long hindcast of the waves, the currents, the water level, because to have solid statistic, we need very long time series. And those hindcasts are validated with all the measurements we are providing. In terms of campaign, then we go again offshore when we construct, because we need to monitor the sea state live. On the top of it, we also procure some forecast, weather and mid-ocean forecast. So we are ensuring we are carrying out safe operations. Once all the turbines are offshore installed, we take our buoys out and we add some wave radars. So that's another technology we're adding on the nacelle of the turbines to measure the waves. Why, you would ask, radars and not the buoys? The budget and the maintenance. We cannot have buoys for 30 years. That's too expensive, though we are missing really the value of the buoys during those 30 years. There's some accuracy issues, of course, with the radars. Yeah.
Okay, so that means you have a lot of in-situ data, Nikolai. So validation of simulations. If you turn to industry, then that's possible.
Yeah, we also have recently a sea ice campaign now in Finland. So we have sea ice measurements.
Sorry, can you repeat?
How close these data are? So are you keeping it for yourself, or you ready to share it with new researchers?
So Natasha, are you willing to share the data, and in what conditions?
I mean, we're sharing when we enter a consortium, which we are gonna do with you, Ivo.
Yeah.
So you will have access to some data, but of course, you can categorize the data into sensitive and not sensitive. Sensitive data, it's quite tricky for us to share, like the wind information, the bathymetry, but waves, sea ice, current, water level is not sensitive. So we share whenever we are asked to. We are sharing with DMI, we are sharing with SMHI, we are sharing with a lot of institutions when we can. And regarding the ecological part, we have an environment team as well that is in many research projects as well, where we share the information. So we don't keep for ourselves.
That's good to hear. Jari, you had a comment?
Natasha, so this is Jari Hapla from the Finnish Meteorological Institute, FMI, and I have to really take the interview because this is the really hot topic about the data, what the industry is collecting. And anyway, a little bit something in background. So everything, the most important data, what we need for the Baltic Sea is the ice thickness data. It's an upward-looking sonar data, upward-looking sonar data. In FMI, we are doing something in the Botnia, a couple of sites, regular measurements. Then a month ago, it was really sort of, I have a international meeting. We had a meeting, and then a Norwegian colleague presenting a data analysis from the Baltic Sea about the ice thickness from the upward-looking sonar in some location, because where we are not doing the measurements there, how come you get the data? He said, from waterfall. So they are doing, I don't know who has done it, but maybe you are consulting with the Norwegians to doing the analysis, and that was quite fantastic. So that was the first to me to learn about it. And this is what I have known for the Arctic, like a Karasi, Barents, there has been oil companies conducting a lot of this upward-looking sonar data, but those are always be classified. And it's a really shame thinking about the detection of climate change, but also the validation of the model. And I would like to really ask, in a way, because of course this industry, usually when the industry making measurements, the industry thinking about the data is so expensive. Of course, if you pay a couple of $100,000 million, you don't want to share. But I believe if you would share that openly, you will get more. The 100,000 euros, what you have invested, you gain more if you give it that free of charge to everybody. And this is then I think that when we are now talking about the development of the Bay of Bothnia, Gulf of Bothnia, you are not the only operator. There are many of the other operators. If you find a model, not a real numerical model, I mean, this kind of sharing model that the industry, this is and science, universities, governmental institutes are making collaboration in collecting, analyzing the data. That would be the best for all. And I don't know how willing you are that, but I think that we have a lot of will from the governmental sides and the institution side to build such kind of consortium or trust on. But I don't know. I just ask about the data and something, because this is the future. You are not the only one who is doing. Okay.
Sorry,
I completely agree. Completely right.
Let's give some space for Natasha to answer.
Yeah, no, I completely agree. And I share your opinion. In our team, we are mainly scientists and researchers. We all come from academia, so we know the struggle. And this data, yes, there's one thing. It's about procuring the data, paying a lot, getting the budget to measure. The second is once you have the data, how do you process? And it's there that we are stuck, and we are trying. I think now we're getting a student in FMI to process this data and give something valuable out of it. So I don't think that Vattenfall is keeping the data for itself. Maybe other developers, I'm thinking about oil and gas. Those are really big companies that have tons of data and are not sharing. But we are really open. We are in so many projects, and I'm really also fighting to share this data. I know it can unlock a lot. And also for us, because we're giving you data, we get better models. So it's a give. But well, I'm just one person in a big organization. So much power is not in my hands.
Yeah, I can confirm that Vattenfall is actually like the rare occasion who is willing to share the data. We have a joint project with them, Digital Twin Ocean for ocean wind energy sector. And I was quite surprised what kind of attitude Vattenfall had. So they were really willing to share the data. So this is a good thing. So if they are coming towards Gulf of Bothnia, then maybe there's a possibility for FMI and Vattenfall cooperation as well. But Lars, you wanted to add something?
Yeah, I don't know how willing the different companies are with this, but I just think, so we've suggested that it should be a requirement from the government that you should, if you apply for, if you write your environmental impact assessment, you should actually share your data. It could be a requirement from the government, and that would make it much easier for everybody to share.
Yeah, Lars, it is the case actually for the Dutch government is monitoring the farms and sharing data publicly on their website. So you can monitor whatever waves, currents, it's all public. So we have this collaboration work with them to locate or find location for their devices, and then the data is shared. There's the same with the Swedish projects, but right now, you know, there's this issue with political issues in Sweden between nuclear and green energy, so we can't build basically. But in the Swedish requirements, it is stated that hydrographic monitoring has to be in place, and data should be shared. Same with the new Danish tender, the data will be shared. So it's going the right way, I think.
Sounds good.
Yeah, anyhow, if the data gets in the digital twins or used for these simulations, then it's, I think, a step forward. But now, turning to Michael. So, expert in modeling sea ice impacts on offshore constructions, vessels, anything that's in the sea. So, what kind of information do you need to assess these kind of impacts in the coastal areas or offshore areas? What kind of level of detail do you need? Is it climate data or something very specific like Jan was showing, or something in between?
You're right that I'm expert in modeling this ship ice structure interaction. Not so much on pylons and those things that I have done only once, and there we were, I think, fairly successful. But there is a kind of important distinction between ships and these fixed offshore structures. So basically, ships have the ability to move. So that's a kind of annoying feature of them, if you think about it. And all these models that you were showing today here, they kind of, I wasn't sure what is the resolution now you can go there. Is it like a kilometer scale, or this last model we saw, I think that was quite in a small scale already. But let's say in this offshore structures problem, what we had, the project also Ilya was showing, was that although we get this loads, or let's say we couldn't get really the load on a structure itself. So because the resolution was too high. In our numerical simulations, we use resolution of maybe a couple of, let's say 50 millimeters or something like that. And I think the biggest problem now between your models and our models is that this difference in scale. And in my previous history, I have a kind of, I'm modeling, let's say, ductile fracture in metals. So that is also a problem there, that you really need to be able to scale between different length scales, or how to bridge those two different length scales. And in order to build, I think, this next generation of digital twins for, let's say, ships at least, we would need to kind of utilize your data in a real, let's say, in situ really, and bring this information into our models. But how do we do that if the scale difference is so big? So for us, that is at the moment the biggest issue, let's say, how to do that. And I think maybe in the next phase, there is some, let's say we have to use some AI and machine learning models to do that.
So the challenge is going from, in the destination or digital twins, we are talking about kilometers, sub-kilometer scales, but you need centimeter scales.
Centimeter scales.
So that's the next step for the impact modeling. So I guess you're not doing it, Nikolai, like global scale, centimeter scale.
Yeah, I think there needs to be some collaboration between, let's say, ship operators who actually are measuring this information on board ships. Kind of, they make visual observations. They use different sensor data, different cameras, so that you can use your models or validate your models. I don't know how you validate your models. Is there some validation, or is it just
with the data that Natasha is providing to the community?
Yeah, so maybe there has to be this kind of feedback loop with ship operators that you can really pinpoint to some location in the sea and see some ship operating there and kind of say that, okay, we think that there is this kind of ice there, but what the ship is actually seeing can be quite different. So kind of this kind of validation would be very useful in some future.
Yes, we have a discussion. Jan.
So my model is we have done kind of lab scale experiments simulated, so with resolution of like 2-3 millimeters. But then of course we can do maybe a cubic meter. But then we go to the one that I showed, then you have a few hundred meters, then we have a resolution of 25 centimeters. If we go to 10,000 square kilometers, we have a resolution of maybe 7 or 8 meters. So the models that I use, they can scale, but of course then also the simulation domain will change. You cannot do millimeter scale 10,000 square kilometers. That's impossible. You would need a computer that's the size of the universe for that. So when you go to the ship scale, my kind of most concrete question is, do you see the ship as a solid body that doesn't deform, or should it include also deformation of the ship, like the hull, how it twists and bends when it goes through the ice, or is it a solid body?
Let's say if we think about some kind of decision support model, then it would be definitely a solid body, because we just want to see in which direction maybe we want to go in the near future. So let's say to save as much fuel as possible. Or let's say the alternative would be that, okay, we sustain that much damage if we go into this ice region. I mean, also our simulation models are very accurate. We can simulate a lot of things, and we can maybe build a surrogate models out of that. So, but the problem really is that if the ship is already operating, what do we feed into these let's say these machine learning models that we have built, so that what kind of ice data we don't have this ice data where the ship is actually now operating. So that is kind of a missing. I think, like you mentioned, that we can build these different models, and maybe the next stage there is to build those different surrogate models and build it up based on that.
So do you mean that you kind of have a computer on board the ship and it's kind of running all the time and telling the captain where to go, or what is it you are?
Decision support is basically like that. Of course, it's very simplified. I mean, it doesn't go into the details and it doesn't run a simulation. It just uses the simulations that we are already kind of ran before, right? It just kind of surrogated into some simplified model that you can use. But the basic idea is that, yes.
Yeah, that's a little bit difficult with a supercomputer.
But that's what we are here for, user needs. So what direction we should go. So we have talked about data and simulations. So what are your expectations for digital twins? Have they made your life easier? Will they make it easier? Or haven't they made it easier yet? So multiple answers, or tick in the right box. So do you think that digital twin technology currently is usable, valuable for you in offshore wind energy, spatial planning, naval architecture?
Maybe I will just continue because we already discussed it a bit. So in ships, it's mostly used for two things. First thing is prognostics. So you could kind of use digital twin. Let's say you measure some data and then you make some kind of fatigue life estimation. Okay, I should do the maintenance in 5 years if I operate in these conditions. So for that, digital twin is quite useful. For this other aspect that we discussed, let's say you have a ship that is operating and you want to use some satellite data, which can be quite inaccurate. So for that, this operational decision support, there is still a way to go, I would say.
Okay, so climate DT would have applications, extremes DT, so. Let's say there are like two ways in destination Earth ecosystem. So thank you. Natasha, you were nodding or shaking your head. So how does it look from the offshore wind energy side? So are digital twins useful yet? Not?
I think there are similar topics with the ships topic as well. But I think absolutely, yes, we're looking towards using more digital twin, mainly because they will allow us to simulate a lot of scenarios. So what if, all these if scenarios. And that will lead to reduce uncertainties we are applying on the design, for example. I think it will also help to engage the different stakeholders with more interactive models so that, we just come to one single database where everyone can just use their data and optimize the decision making. That's also very important because we are working in dynamic marine environments where we have to accelerate or be very fast in decision making. Right now in Vattenfall, we're having some initiatives. So one of them is, of course, the research project with Baltic, these digital twins of the ocean for offshore wind energy. But in Vattenfall, we're having a project on the monitoring of turbine performance. So we are looking live at the performance of each of the turbine. So we have an idea of when we have to curtail them, when we have to stop. There's also we're also trying to implement multi-use of the offshore wind farm. So it's not only turbines sitting in the water, but also adding. Right now we have a project where we want to have floating solar panels, so having increased use of increased energy production, but also implementing some aquaculture. You probably heard about a project where we are growing seaweed between the turbines in the Danish waters. So their digital twin is really helpful to understand how we can optimize our energy production and also optimize our vessel travels to the site for maintenance, for example. So all of this, it's in the aim of course, reducing fuel consumption, but also optimizing our time offshore.
Okay, thank you. And Lars, are digital twins useful or useless?
No, but I see a potential there. For example, if we focus on climate DT, I think the good thing there is that you have this, have a global model that you can run with high resolution in a region, for example. So you have this really connection between the global scenario and the regional scenario. Also that you have the coupled ocean atmosphere runs at the same time and with ice as well. So I think that is valuable. So I think, sure, I look forward to seeing good results there. And we can use them for digging even into higher resolution, like closer to the coast, and also looking into wind farms and other ships, for example. I think it can be valuable in the future.
That's well said. So let's conclude with that statement. They can be valuable in the future. So with this positive note, I thank the panelists, Natasha, Mikael, and Lars. We are late for lunch, so let's conclude for this session, and I hope you will be back in in 15-20 minutes. So at 15 o'clock we will be back. So once again, thank you for the panelists and thank you for the audience.
Segment of today, and it's our second panel for today. The first panel looked at the infrastructure, and now we are looking on the other side. How does the cryosphere affect the lives of people living in these areas where ice happens? And Till, the floor is yours.
Can you hear me now? Good. Okay. So yes, thanks for letting me moderate this session and for hosting this at Baltic and others. I would like to invite the panel for this. The first one is Patrick Eriksson from the Finnish Meteorological Institute and the Ice Service there. And the second one is Jari Habala, also from the Finnish Meteorological Institute, but more on the science side of things, but also with a lot of experience in sea ice. And at last, Kjell Quisgaard, I hope you're there online.
I'm with you.
Good, thank you. And thanks for joining from Copenhagen. And he's also from DMI, just as I am, but from the Ice Service. And we will take a look at how does ice impact on shipping and on how is ice used, but we'll primarily focus on the shipping part. And I would like to let you introduce yourself at first, both on how what's your engagement in it and how you see yourself, or how the ice services see the life on ice and the shipping and how it impacts. So Patrick, if you start.
I guess this is the microphone I'll have to use. Thank you. All right. Good afternoon, everybody. My name is Patrick Eriksson. I'm from the Finnish Ice Service. And I don't know, as an introduction, I would maybe start by saying that my education background is in oceanography. And when you study oceanography in Finland, you end up in cold places, so to speak. And so Arctic conditions and sea ice has been on my work table since the start. And the Finnish Ice Service, as quite a few you may know, is monitoring the sea ice conditions in the Baltic Sea. on a daily basis during the winter. We do that partly together with the Swedish Ice Service. So the ice charting is shared with the Swedish Ice Service bi-weekly. And then we do individually, and the services individually do other kinds of services like forecasting and satellite image processing and delivery, and then a number of even commercial tasks for the industry. So it's a quite variable work field for us. Those who are more interested in details, we just published a paper in Frontiers, so you can Google it, the Finnish Ice Service Frontiers paper. It was 1 month ago. It was issued, so I will not talk more than this about that. You can read yourself in our new published paper. So much for advertising, and yeah. And your question was how we.
So how do you, as the ice service representative, see the Baltic sea ice and how people use it, and what's your role in that? Right.
Yes. So how we use the ice, or how we tackle it, maybe, because that is one part of it. The primarily reason for our work is to support the ice breaking operation. So guide them, provide them with information and data, and that is all kinds of in situ and monitoring data, as well as forecasts. So that is one part of it, which has a heavy portion of safety issues. So maritime safety is one of our primary motives to support, and that goes through the whole ice breaking operations, where we in a way are a part of. But then again, we have a large population along the coast, which uses the ice as a means of transportation to some degree. Less nowadays, unfortunately, because of changing climate. But there's also quite a bit of entrepreneurship in along the coast. So we have fishery, and we have recreation as well, and recreational tourism. So and this is where we need to, in some cases, find the ice for these purposes, and issue warnings if the ice is not strong enough, for instance. And last winter, for instance, was a sad example of this. We had a lot of drownings, both in the coastal regions and in the inland lakes. Even if ice thicknesses were, in a way, sufficient, according to the rule of thumb, the quality of the ice, the strength of it, was not what it usually is. So there's a huge spectrum of varieties in the use cases. Okay, I'll end there. Yeah.
Thanks. I would like to move on to you, Kjell. So I assume that the Greenlandic or the Danish Ice Service has some of the same purposes. How do you see both, well, your own role, but also how, and your engagement in it, but also how the Greenlandic Ice Service is servicing its users?
Yes, thank you so much, Till. Greetings from Copenhagen. First, very briefly about myself. I'm a senior ice specialist. I've been with the DMI for more than 30 years, actually with the ice service for more than 30 years. So, and we're providing sea ice and iceberg information to shipping in the Greenland area, in the North Atlantic area. So what does that mean? That's regional sea ice charts. That's an iceberg limit for South Greenland. That's inshore ice reports, text bulletins, ice information in marine forecast, that type of thing. But also more recently, we're also providing more and more advice to shipping. So what is it that we're seeing? I can almost repeat what Patrick said, that if you're interested in cold places, you end up in cold places. And I can fully say that that has happened to me too. But the cold places are not as cold as they were in the past. And we also see that with respect to changing climate, that the ice regimes are changing. So, and that's also meaning some changes to the pattern, to where ships can operate. Opposite to the Baltic, in the Greenland area, we are not serving icebreakers. In Denmark, we don't have icebreakers. The ice in the Greenland area is of a thickness that you would always like to avoid the ice. You don't break the ice unless it's less than 70 centimeters or so. So, but you're dealing with very thick ice in certain areas. But that has also changed over the past 5, 10, 15 years. So the ice has become more dynamic, and this unpredictability of the ice has also become a topic for the marine community. So long story short, we are living in interesting times where things are changing rapidly, but we're also trying to take advantage of new technology coming in. I'm not sure I answered your question, Till, but I made you all more confused.
Maybe it was also mostly to get into introduction to how you work with it, and so that's fine. Thank you, Kjell.
Yeah, maybe I should mention that we are purely based on satellite data, heavily relying on near real-time access to synthetic aperture radar like Sentinel-1, RadarSat-2, RadarSat Constellation, PARS, TerraSat-X, Cosmo, first generation, second generation, that type of thing. So we need systems where we can monitor the sea ice and icebergs in high resolution, where we can have near real-time access to data. The ice is constantly moving. So we need to have a short delivery time of the necessary data for monitoring. And when it comes to monitoring, also talking reports to ship, because as mentioned, ice avoidance is really the key topic in the Greenland area.
Okay, thank you. I think I would like to go back to the data in a while, but let's introduce Jai as well. Your engagement into sea ice and what your sort of approaches in that, and how you see the role of science maybe in FMI inside.
Yeah, maybe my engagement for sea ice. Most important things, I like fishing. I like ice fishing, and also the deploy nets under the ice during the winter time. For me, the ice has been always from childhood a place to be. But of course, when I started to do a PhD, so I got the position about that they're doing a sea ice simulation. Since that time, I'm become to be an expert on sea ice physics. And then there is an application, climate, question is one application. Developing operational model is another application. Developing, safe shipping tools for safe shipping is another application. So background as a physicist is more like applying my knowledge to the well-defined problems of the society.
Okay, thank you. And how do you see that the science can contribute to some of these issues that the ice service, or what the ice service wants to do?
Of course, the most important things is that better situation awareness. Like research is always that we develop the systems to observe and monitor. Now the most important is that satellite. And we have experts which are developing the satellite sensors and the satellite algorithms, which are then using for everyday life. Then, or the operational, but then it's a forecast, and the forecast for the next hours to the next decades or the next 100 years. And then we have to have a different models for different applications.
Right. Thanks. So going back to the data I mentioned before, I'm not sure if this is for Kjeld or for Patrick. I think you get the same issue, but as you know, there are more and more satellites coming up. How do you envision that you should handle that? Maybe you can explain how you create an ice chart at the same time and currently, and elaborate on how that should change.
Maybe I can start on that one. So yeah, it's right that we are heavily relying on satellite data, especially synthetic aperture radar. Not just one satellite system, but more satellite systems. But we also in the good position that the new satellite systems are becoming more and more advanced. So they are also providing more and more details, which are necessary for safe navigation in ice-covered waters. The downside of having more access to more data, more detailed data, is that it takes up lots of bandwidth and data space. So the data management is really something that needs to be addressed very carefully, because it's a huge issue. So and that's I think most ice services around the globe, that's one of their challenges. That's really to do data management, to make the ice charts, to make the data available for analysis. There could be a manual analysis or automated analysis. So and one thing we have learned in the ice service is that we would like to have more and more data also in the future. But our ice analysts, they cannot handle anymore. So the old traditional methods are no longer working. They're working okay, but to a certain limit. So to take advantage of the higher resolution data, more and more data, new satellite systems coming, etc., we need to work smarter. So over the past year, we have been looking towards our science colleagues to see what work they're doing in artificial intelligence for automated analysis of SAR data, and that has really been an interesting last year. We have had doing our own analysis, but also working with other ice services, and maybe most interestingly, to work with some select users on the current status of the artificial intelligence methods. So we would very much like to take advantage of the huge data sets that's available. But we also need to invest in new methods and new technology.
All right. Yeah, thanks, Kjeld. If I continue there, there's not much to add, in fact, from our perspective, because that's exactly how we see it too. And whereas we only have to go 10 or 20 years back, where the bottlenecks in the services were to get the satellite data timely enough to the user, where also the data delivery was an issue. These things are now solved already, and our icebreakers, for instance. Okay, we talk about the Baltic Sea, where you're close to coast almost all the time, but still it's a different thing in the Arctic. But still on that level as well, there are good solutions, and we are facing these new challenges that Kjeld mentions, that an overwhelming amount of data, where the ice analyst's input needs to be rethought, because also the products of a few decades back in the ice chart, in the traditional ice chart, is starting to get I don't know, or needs to be rethought in some way, because the usage is a little bit different. It's more tactical in a manner that is different from 20, 30 years back. So and at least in our institute, I would say the way of working now is to really concentrate on the interaction between science and services, to get the scientific results, even if it was, I don't know, modeling or satellite image analysis or AI solutions, to the ice analyst's drawing board, and that way creating the most useful products to the end users. That is, I think, the new challenge here. Yeah.
Do you have anything to add, Jari, or should we? Okay, no, good. Well, then let's continue. So we've heard about the satellite images and their connection. The climate DT is mostly on the forecasting issue. Oh, okay, I can't see that, Kjell. Sorry, it's.
Oh, sorry. Yeah, I had a hand, and that was actually an add-on comment to Patrick. And it's about providing this feedback from, to providing this AI information from science to the ice analyst. But I also think it goes the other way around. So the people with the operational knowledge about how things actually work in daily life, that they provide the input back to science. I think it's very important to close the gap between science and operations, but it's a two-way communication.
Very good point. Yes.
Yeah, thanks. And okay, then I would like to move on to this particular project that we have here. You have probably heard of some of the services that are developed. And I would like to take a little bit look at how useful you think they are, and in what cases, and maybe also look at what is the resolution needed, both for I mean, I know for present, but more for the forecasting part of it. Where do we have to go? For instance, if Nikolai has to set up a new model with he tells us around 1 kilometer. Do we need more? Where is the limit? And Patrick, if you could start with the pressure and ridges that are developed within this, how can you see that being used, or also for future predictions?
Yeah, thanks. And this is one of the crucial things in the Baltic Sea, or let's say the ice breaking or the ship assistance operation in the Baltic Sea is how to treat the deformed ice, or how to tackle the deformed ice and ridged areas. Because and this is a question. Your question is something I've asked the bridge officers as well. What is the form of forecast you need from your perspective? In this case, they mostly first mention the satellite images, the SAR images, where they can see the ridged areas. And then even if they have a weather forecast, they can do their own, in a way, their own prediction on the development, or what areas are the crucial ones, the most difficult ones within a day or two. So I really haven't had any good answer from the bridge officers in this respect, and we have even introduced a number of products, and one of them is maybe the most used now on board the icebreaker bridge in their system called IBNet, where we provide the satellite imagery and the ice forecast, and there also a drift model and deformation areas, because they are focusing on these certain shipping lanes. This is maybe one way of working, but I would certainly like to develop it a little bit, because the time, I would say the temporal resolution or assessing the timing for risky situations is maybe one place to focus on, but really I don't know really, but but I have to say that the deformation, ridging, and certainly pressure in ice is maybe more important in this respect. And there we have some kinds of map solutions which can maybe be the best ones. At least we haven't got any ideas on anything else.
Thanks. Yeah, I do see a solution for this if a forecast model, maybe using systems like GANs and how to scale that up to.
Well, of course, we have to really make a distinction about the forecast. I think Patrick, now you are talking about the short-term forecast, like a synoptic scales from the hours to 5 days max. This is for the operational window. And for that, we have the usually high resolution models, pretty could be quite sophisticated sea ice models, are really tuned for the different sea ice models for the Baltic Sea, for Canadian waters, from the Southern Ocean. They're very models which are tuned to be the best models. Now, when we are talking about the climate DT, in the climate DT, although it's close to the resolution of the operational models, it's not the operational model in that sense. So it's produced a climate. It doesn't really can use any kind of like a tactical navigation. So and it's not the day to day. So they are projection of the future, and they are probabilities of the future. They're not the one number. They are probabilities of the future. So maybe innovative, because this is now the DT climate. So should we talk a little bit more about what are needs of your clients in terms of the climate product? And then if it go in a little bit to that direction, then I see that for the climate DT would be really the first climate simulation which has potential to provide understanding about these extremes. You was talking about the ridging and ice pressure. That is unfortunately, it's not safe. So in a way, what Nikolai presented in the model, in principle, it resolved the ridging and pressure on ice, but it's not safe. I think this is the question that it's just there's no space. But if the idea of the DT climate is that the users, which, for example, need the ice pressure ridging information, they can be engaged on the production cycle of the climate projections in future, that they can have the subroutines and models which can calculate these kind of extremes like ice pressure. And this is a good example, if you're talking about the CIMIC, probably everybody have you heard about this is the IPCC CIMIP experiments. All the climate model centers are producing the climate projections. They are called CIMIPs. CIMIP 6 was the last one. And this is very much of the use for climate adaptation studies. But the CIMIP models they usually produce monthly means, some parameters, quite many for the sea ice, but not for the ice pressure. With the climate DT, we as a science, we could go be in a same rhythm when the climate projections done it and put our such kind of process models which are needed a client, which are needed information which is not saved. And then anyway, all the comments what you say, what do you think? What are the important for your clients or for yourself? Also for important for us, because then we can develop these submodels to get that one. And so we can speed about the rhythm. If you think about now we are looking about the climate projections, and once in 5 years, new projection, doing a process study. So it takes climate DT will be in the future much more faster than, people like you ask about the questions that then people like me, then we get engaged with the people like Avi, that, okay, let's do that one. And then we can have for you and for your clients results much more fast. That I see. I think that all the things what we have seen today is a demonstration But after 10 years, I hope that the climate DT will be realized, will be a long-term, a new kind of climate projection. You know, I don't know, way to make a climate projection.
So do you also see a way forward in terms, I mean, it's probably too expensive to run all the climate DT simulation, as many as you run the CMIP.
Yeah.
You're never going to get there to have both the high resolution and the multiple ensemble. Will there be other ways around? I think we heard hints a little bit about it earlier.
Of course, machine learning, machine learning, and think about it when we have. I think there we have to be very, very careful. Machine learning is, it's I can get garbage in, garbage out. But you have to know what you are doing. Of course, you have to have a good training data. If you are using a model data which is not validated for the training, then it's more like a garbage in, garbage out. Nice figures, nice things. We have to really have observations, real observations, or a model which really we believe and trust it. So this is I'm not a big fan of the machine learning techniques because of it's a statistical method. I'm more like a physics looking the best, but I have seen the fantastic applications. But one have to really carefully when they apply that. It could be very fast way to produce results. Yeah.
And of course, if anyone has questions from the audience, please speak up. So if we tackle along that, if we should create training data for both for validating current models, but also for then would it be possible to do some of that from some satellite images you're already looking at in the ice services? If you needed pressure reaching, like you say, Patrick, on a larger scale, could that be a thing that could, or Kjeld for that matter, if you have the
Maybe I said this is we're discussing about a little bit about industry. I think this is also that now we have a possibility in a way if you could get engaged on industry. If you think about the shipping, it's with machine learning techniques, we can instead of the produce geophysical information. I mean, geophysical is like ice motion, deformation, pressure, thicknesses, and so on. But we can jump from that level to the upper level if you have information about how the ships are navigating nice. If you know that they're like a ship classes, how the ship engine, if you have good information about how much the power the ship is using, related to that ice conditions. And then we can relate it about our environmental observations, model observations, directly to how the ships are behaving, how the ships are navigating ice. And for that, the AI would be very good. But then we need the data on how the ships, what is the power of the ships, how much the energy they are using. And this is classified information. This is I think it is collected by all the companies which are making the ship engines and all the the data is collected. I don't practically all the ships are collecting the data, but it doesn't want the people or the companies doesn't want to share it because now it's think that the data is value. So that kind of if we want to go in that direction, there should be a more open data policy from the industry too. And I don't know how we can influence on that, but maybe you have the better experience about that you are working much more about the shipping companies.
I think I would throw the ball to Kjeld because he's working much more directly with the shipping companies.
Thank you, Patrick.
You're welcome.
Okay, no problem at all. So I think it's very area dependent because in the Baltic, the icebreakers they probe through the ice. But if you're going into the Arctic area, it's a different story. Typically, as I mentioned a couple of times here, that it's ice avoidance. Most of our clients they tend to avoid any ice simply because of the thickness of the ice. And talking about ridges. Ridges in Arctic waters, they are interesting, but you don't go through with a ship. That's simply not gonna work because there's a certain portion of the ridge that's above water, but most of the ridge is actually below the surface. So a 5-meter ridge is really something that is not as a ship is not able to penetrate. So I think, but what I'm missing here is really some field work, some field programs that are targeted these things because. There was one mention that the ice service, the ice analysts, we can see ice ridges. Yes, we can, but we don't really have some data sets where we can see, so we can validate what is it that we're seeing, so we can quantify it. I think that's important. So one thing is to quantify the ridges. The next step in this is, okay, so how do we quantify ice pressure? That's very, very difficult, but of course an area of interest because we also see more clients coming into our waters, and also with some ships with some pretty heavy ice class. So we will also see more ships coming into Arctic waters in the future, not just to the ice sets, but go inside the ice sets into the ice pack.
Okay, so maybe that leads on to the next. So there's also been looking at a risk index, Kjell, in this, and that's based on concentration and thickness, like Xingfang presented earlier. How do you see that in a future model prediction? How is the usefulness of this? Should we add? I mean, it's not going to be in this project, but should we? What should be looked at to make it better? If we need more parameters in the risk.
It's important to bear in mind that safe navigation is not just a question of ice concentration and thickness. There are many other parameters. We have discussed ridges, we have discussed pressure, but it's also weather, it's current, it's also the training of the navigator. It's also the strength of the ship. So discussing the RIO indices, they are developed for, there are the different RIO categories for 12 different vessel classes. So that's a good start. But it's so important to bear in mind that these RIO index maps, it's not a standalone product. It's always something you have on the side where you have the complete picture, and then you have the complete picture that is transferred into a RIO index map that may show up red or yellow or green, where it's safe or a no-go area, or there are some special considerations. So we have done some experiments with mariners this year, where we have converted our regional sea ice charts to RIO index maps and sent them out to mariners. And one thing they said that they were missing is not actually, well, the colors are fine, but it's actually the RIO indices, the individual indices for each polygon they're interested in. So that's a learning exercise. On top of that, we should always bear in mind that calculating RIO is not just it's not useful for large polygons. So it has to be on a certain level of details to make sense for the mariners. But for very dynamic areas, that's also a challenge, because if you do an ice map once a day, the ice polygons will change, and also the ice conditions inside will change, and that will impact the RIO index maps. So it's difficult. So and that's also why it's needed to be put into short-term forecast models if it should be used for mariners. So there are many aspects on safe navigation. So of course, concentration and ice thickness are two important ones, but there are many others as indicated here.
I can really think that one application of the using TT climate data and RIO analysis for example, if there will be a company here in Tallinn which is planning to make a regular, shipping from Tallinn to, for example, Churchill. Churchill is it's a small city in Hudson Bay in Canada. So that, and they are building for Churchill a new railway to the Canada west coast. So that is what potential new way to transport goods from Europe to North America and to the Pacific. But anyway, then is a question that the climate is changing. What kind of vessels they need? If they plan to, if they want to have the full year operations, so that they need a vessel which is coping in the sea ice conditions here in the Baltic Sea, but also sea ice condition in Labrador Sea and Baffin Bay. That's Hudson Bay. So then with the climate DT data, one can calculate the probabilities for different ship classes. Do they need the PC2 or PC3 or PC5? Then they calculated the cost. PC2 icebreaker is much more costly than PC3 or PC5. And then they can make their decision. They think, okay, all right, if they pull a 100% guarantee that they can always cope the ice, then they put so much money on the table. If they take something like only 90% service level is good, then they say, okay, then they can have the smaller icebreaker. And this is because then this is the DT climate is enough high resolution to resolve the sea ice characteristics in Hudson Bay and Baltic Sea and so on. And this is that's one model, consistent model. Now, in a way, if somebody want to do that kind of things, then they want to have getting somewhere and download the data from the Baltic Sea forecasts, then for the Hudson Bay forecast, maybe also some other forecast, make a combination, and it could be a big mess, different projects. So this is the climate DT could provide a globally coherent data for the decision making, like that. Using RIO, and RIO is defined by the what is this classification societies. So that's I think the one way to really utilize the RIO. RIO is not good for the daily forecast, like I say.
Yeah, can I hold on to that? Yeah, so maybe if you can give me or the audience the impression of what would you then save more than the concentration and the thickness, because it's we don't want to rerun it all the time every time we have a new customer. And but if you could maybe name a few other parameters that are important for the RIO index or for the, and we can't train them. Yes, you'll have the chance to kill it in a minute. Yeah, but I mean we can't put in the training of the mariners. That should be someone else's task in this. So
what do you actually ask? What is that?
What would you save in the climate DT more than concentration thickness?
Yeah, age. This is really the fraction of the multi-year ice. That's the very important. That's the very important parameter.
Okay, thank you. And Kjell, you had a comment?
Yeah, maybe I can add that where is it that ships get stuck in ice? That's in the thickest ice, in the ridged ice, or where there's heavy snow. And especially for Antarctica, we should bear in mind that the polar coat is not just the Arctic, there's also Antarctica. And the ice is very different down there. And one thing I've learned is that snow cover is really a big issue for shipping, for ships going into the ice pack in Antarctica. So ice strength, ice ridges, and snow cover, that may be some interesting parameters. So right now, when I'm doing some climate predictions my own way, I look at the statistics, 20, 30, 40 years back. But that's in times of climate change, that's not the best way you can actually do predictions, by looking backwards. But this is what I have. So I see there is some potential for development here with the climate DT.
Thank you. And can you promise us that, Nikolai, that you save those if we ask you?
Well, I mean,
cannot promise.
Sorry.
I cannot promise 100%, but certainly something that we can, like, especially if it coming as a request from the users, because Climate DT and eSIMWF are very kind of, while they listen to what the users actually want. That's one of the idea of the Climate DT, that it's interactive. And Jari, how you, as you said, that we, like, I mean, there is a chance for the researcher and the people who use this data to impact climate simulation, what kind of data we produce, what kind of scenarios we produce, and additional variables is, of course, part of it. I mean, the philosophy there is that we save just the variables that are, like, it's called generic state vector, that are describing the state. So if you can compute something from the UNV, for example, like stresses, then you probably should do it offline after it's saved. But I mean, things like sea ice, snow thickness over the sea ice is something that you cannot compute, right? And something that you have very good arguments to have as one of the parameters to be saved. Ice age, I'm not really sure. That's maybe something that one can also infer afterwards. But snow is snow on sea ice is actually a very interesting point, and we certainly will consider that.
Thank you. I think time is running out, if I remember correctly. Yeah. Oh, I thought it was 45 minutes, but that's okay. We'll see. Yes. Right. You don't need to use all. No. So we've looked at other downstream services for this, and how would you explain the users afterwards, the results? I mean, how will you? One thing is that the science can come to the operations, which is now, and say, this is what happens in 20, 30 years. Can you give the same descriptions to the next level of users? Because you are somewhere in between the science and the user community, with either icebreakers or shipping companies or manufacturers who builds ice vessels in ice. How will you communicate that? Okay, I get a risk index. It tells you that you can propagate 70% of the time through this ice if you build it like this. But what is the uncertainty? All of these kind of things. How will you?
This is I think that this Rio index, this is very good, because we me as a geophysics, I learned it from the naval architects. From that, so they told about that, and we have adapted their method. So that is, in a way, this is the good way to I don't need to tell them what is the Rio index, because they know that they better. They are just good, then it's more that what I need to, or we need to really say the uncertainties, because the Rio data is designed based on visual observation from the ship. This is the basic things, that it has so many parameters which are based on visual observations, and from the models they are just limited amount. So our model estimates is a simplification of the Rio index, but it's an estimate for the first decision making. Yeah.
Okay. And yeah, Kjell.
Yeah, maybe I can add. I think you are touching on the right thing, uncertainty. But I would like to go a little further, because before I go to the marine community, I would like to learn more about the methodologies and the limitations, because it's very important to know and understand the limitations, so these can be communicated to the mariners. Because if they are going to design a new ship or buy a new ship, that's a big decision on a 30-year horizon. So that should be a sound decision that is based on some very substantial work. Where so okay, what exactly is seen in the data and in the systems, and what is not seen. So that decision is made right.
And how do you see, Patrick, when in a future where Baltic may be, well, sometimes ice-free, what are the challenges? Is it new hazards or are there some of the same ones? What should you look out for? And
yeah, this is really a good question and a timely one because here as the variation between winters also starts or most probably starts to vary from very mild to possibly then severe every now and then. I would say the most important thing to focus on is preparedness for these more difficult conditions that still will appear. This is something we discussed with Jari in the morning, and it does not only apply to when I look at the Baltic Sea now. It does not only apply to the northern parts where we most probably will have ice every winter now for until the end of the decade, but century. But even for the southern Baltic, where the preparedness has been already diminished, and there is, I think, a focus area which should be tackled in some way. I'm not quite sure how that should be done, but I do think that the climate DT could be one really relevant tool in this. Having watched the presentation during this day, so using that information for the preparedness planning, maybe that could be one thing to look at. Yeah.
I mean, one thing is to make an example of 100 models. Another thing you can do is to, let's say, take 10 years and say this is the same climate. Would it help you if you could say that 3 out of 10 years there's ice in this region or something like that?
Yeah, I think that would be the way of doing it, utilizing the data that you get in the DTs. Yeah.
Yeah. Yeah.
So it's more like a question to everybody here that I often hear this that, okay, so it's getting warmer now, so the ice is going to vanish. But I have the feeling that the climate change might also increase variability in winters. So is it really going to be so that it will diminish to have these harsh winters or not? I wouldn't be too sure about that. It might be that it become even worse.
Do you have a... Well, thanks, Patrick.
Yeah, this is a really great question. So if you think about it, in general, we have the planet is warming. In general, the Arctic area is warming 2 to 4 times higher than the global together. But then we have the interesting dynamics events. When, for example, this is really the big debate question that when the Arctic sea is shrinking, is that the triggering more like atmospheric, circulation changes on this jet stream? So the more that we have this kind of patterns that we take cold air outbreaks from the Arctic to Central Europe, or the blocking situation that, when now I'm talking about this kind of anomalies within the monthly to 2-month scale. We know that in Baltic Sea that the most severe winters are occurring this kind of situation, that we have a huge blocking situation, that this is really the high pressure system is standing over the Baltic Sea at its cold period. In that time, there is snow in even, France or Rome and London. I don't know, is the DT climate model better than the CMIP model? Because CMIP models, because they are too coarse, they cannot produce such kind of a dynamics correctly. Maybe Nikolai, could you say that have you looked about your DT climate models, this kind of internal variability or the seasonal anomalies? Can you see that is there any kind of, first question, are are the DT climate, like atmospheric dynamics, but is that better than the CMIP models? Is it more dynamic? And then have you seen any trends on this kind of internal and variability, Arctic mid-latitude linkages?
Well, I mean, I don't think that anyone yet had like very deep investigation of this question, and it's very hard to answer the question. Is the atmospheric dynamic is better than in CMIP? In what sense, right? So, like there is this indices that we compute in order to compare the historical simulations to the data, right? And how the variability looks like and how the mean state look like. I mean, these tables. And we compare usually with the CMIP6 model mean, and all of our models are better than CMIP6 model mean. But you've seen some of the CI's results from our models, and it just shows that it's not that difficult to beat the CMIP6 model mean. So I would say that our models are very good quality, relative to CMIP6. But if they are kind of resolve all the dynamics and all the effects that you're interested in, I mean, there's still a question that we have to answer together. Because I mean, in Destiny, unfortunately, there is not much resources for scientific investigation of this data. So if you manage to get through the hurdles of assessing the data of Destiny, I mean, it's the whole bunch of Nature paper that you can immediately write if you want to, because I mean, not many people actually looking at this data. So I invite you to actually look at these questions yourself and try to figure out it. But I mean, the potential is there, right? So the whole idea of high resolution models is that we go closer to the first principles and we're supposed to simulate these dynamics. But I mean, how this holds in reality, for some of the effects, it does, but I mean, if there is any upscaling effects that makes the general climate better, I cannot give you like very good examples. There are some things in ICON where they fix the double ITCZ, for example, but things that are striking, let's say, again like Nature paper level things that say, okay, we definitely see it better than any other low resolution model. I would not say that. Of course, the local effects is absolutely different. I mean, you cannot really see and look at the Baltic Sea in the CMIP models, right? So it's like 3 or 4 grid points, and that's it. So I think already from this perspective is a different story.
Okay, maybe I continue a little bit about that. What is really one thing, the answer for your question is that the very interesting thing with this, not so much, it's much talking with the oceanography, but maybe not too widely. So quite much you have heard about the talking about the North Atlantic circulation, AMOC, and the collapse of the AMOC. Well, I think this is quite much crap, though. Forget those. More important is that the word called Atlantification. This is the like when we have the extension of the Gulf Stream, North Atlantic Stream, Norwegian Current to the Arctic, and that has been enhanced. So there's more and more ocean heat going on from Atlantic to Arctic. Barents Sea is ice-free. Kara Sea is coming to be ice-free. We can see also in Laptev Sea influence on that one. And because this is then if you look up at the map of like Finland, Scandinavia, we are like a peninsula. If you write projects, look at the peninsula. We have the Atlantic side, North Sea, Norwegian Sea, and then in north it's now ice-covered seas. But in the future, if there are ice-free seas, and how much that is influenced then the local circulation, that's a big question. And this is really the present climate models cannot really resolve this one. And I think that this is the potential for the DT climate, high resolution. It's very much the ocean processes, ocean sea ice processes, which impact then the atmospheric circulation and so on. Yeah. And this is then thinking about the decision making, about the what is the really extremes and how these are changing. So if you design about something over there, you know, offshore wind farms in the Baltic Sea, you have to take account about what is the most extreme ice conditions every 50 years, and that depends on the atmospheric circulation or what is icebreaker you need. Unfortunately, we cannot answer that correctly yet. Oh, I would be very, very uncertain to answer about that question now.
Yeah. I think we are wrapping up now because we managed to get a good discussion going. And thank you to the panelists for participating and for the rest of you for listening in. So yeah, thanks a lot.
Thank you. And it's time for the last session of the day, which is a practical one hosted by our DT colleagues from BSc Barcelona. So Diana, the floor is yours.
Hi, thank you. Okay, so thank you for joining today. This will be a more interactive session. My name is Diana. I work in the Barcelona Supercomputing Center. And first, I will give a really quick presentation about the work that we will be doing. And then we'll start to work in different groups, both online and here in the room. So, yes, our work in this pillar from the Barcelona Supercomputing Center, we're working in the knowledge integration team. So first, a really quick background from the BSc, because I think in other pillars, of course, you're working with the rest of the modeling team and in the earth sciences. We're all in the earth sciences department. So in general, our objective is to develop and implement global regional state-of-the-art models. But we're a huge team, like we're more than, I don't know, 1,500 people working at the BSc. So we're really lucky to be together on this because we work in different sub-teams and groups. So Sarah, Antonia, Marta, and me work in the Earth System Services group that we work focused especially to co-design climate, air quality, and health resilience services while facilitating knowledge exchange. So in this pillar in specific, we're working a lot in trying to understand the user needs, the challenges, trying to use different design thinking methodologies to understand how could we present, share, and communicate to the different users, but also to the general public. So we work for a more resilient and sustainable society. We think together, working together is the best way to solve complex problems. So we have all different kinds of backgrounds. My background in specific, it's from product and service design. So we design the different products or different media or applications or whatever needs specific on in each project. And we use human-centered design, that it's through qualitative, quantitative, and participatory practices to identify the trends and patterns that the users and the public at the end will have. So it all begins with understanding like what motivates a group of people and why. These are just some examples of like finished products that we have worked in the past. So this is an air quality forecast system. It's one of the models that we work with in the Barcelona Supercomputing Center. That is for air quality for different regions. And we made like from the website, but also like all the tool to explore the different pollutants, air quality index, etc. This is another example for the Barcelona DOS Regional Center, that it's also the different products and forecasts, how to explore different models, probability of exceedance, evaluation, observations, etc. But to arrive to these kind of products, like we work together with the users to first interviews or participatory practices or some of qualitative and quantitative approaches. I don't know, sometimes it's like for a year of just exploring, talking with the users, and then like at the end, getting to work with the design, to some wireframes, some low fidelity prototypes, then we arrive to the high fidelity prototypes. But everything depends on the user experience research. For example, this is sometimes we don't even know what we're going to design or what we're going to work with. We're just having a vague idea. This is another example that it's called Greener, an European project, where at the beginning it was just we want to create a digital product to help students from 10 to 15 years old understand more about air quality forecast, etc. So almost 1 year of research with different students from all over Europe, with teachers, with parents, with researchers. We came to this application that it's kind of like a Duolingo with augmented reality technology to understand air quality models and air quality data for really basic public. So these are just examples of how it's a finished product, because right now we're in the beginning of this with this project, but we want to show you sometimes it's easier to see what can be done or not, and understand why we're starting talking with you and with the users of this of the Terra DT and NOCOS projects. This is another example. It's an EPI Outlook. It's a project focused on epidemiological indicators that have different indicators for climate suitability for different vector-borne diseases. So in this case, you can explore the different time series. You can see the climate drivers from each one of the indicators, the different vectors, the anomaly maps. You can add layers of socio-demographical layers to understand who will be the most vulnerable societies or people with this specific suitability for transmission of this disease. And you can see all the information, the climate information inside. You can see the yearly insights. You can go and see this is going to be a warmer summer than the past 10 years. So this specific vector will be more suitable for transmission, or these kind of questions. But all of this is inside the framework that we use, that it's design thinking. We use the Double Diamond framework coined by the British Design Council. So we're right now in this project, like we said, in the beginning stage, in the discover one. So we try to understand what are the problems, what are the main challenges that you face, so we can develop different solutions like the ones that I share with you now. In the discover phase, it's this part of interviews. I think I sent a lot of you emails, and I'll be spamming. Please, if you want to talk with me during this workshop, or if you don't have time during the workshop, we can also talk on Friday or next week. Right now, we're just like, we always say, like, we're trying to have coffee with people, understand, talk. These are informal conversations about what are your needs and your daily challenges, so we can communicate it with this digital product that we will design. So for each part of this double diamond, let's say in the discover phase, we have different methods. So one of the methods that we use a lot in UX, it's the UX user persona. I don't know if you have explored this, but it's kind of, we always say that it's like having imaginary friends that we create together with all the user needs that we find. So in this specific workshop, I think the profiles are really interesting for us, because we want to create different groups to work together on different personas. And online, Sarah and Antonia are now, for one understand, connected, and we'll also have an online group. So personas is, we try to map, like, what are the main challenges, what are the main goals. We're really, really interested in the use cases, and I have already seen some in the presentation, so I'm really excited and will connect with a lot of you soon. So these are the examples of the user personas and the empathy map that we make. This is, for example, the ones that we did for the Barcelona dos Regional Centers. So we're trying to understand the different users. I don't know, for this one, we were thinking of people working, for example, in meteorological, the state of Spain Meteorological Agency, people working in modeling systems, and people working more in networking and dissemination. So we try to put together all this information coming together from the surveys that we have already started in the user consultant group. Today we're going to be working in this participatory workshop and in the interview. So all together we try to understand the users really, really deep, like what are their goals, what are they listening to, what are they hearing, what are they using right now. Well, we try to map everything, so at the end, whatever product that we design, it's going to be based on the real users and the real user needs. So, well, this is at the end, but let me just check that we can use my link now for the people online. Okay, Sarah is then taking care of online. Okay.
Yeah, I'm switching now to the link and Antonia is already there. So see you later for the reporting back, maybe at 45.
Okay, if it can be at 40, so we can have time to listen to everyone there and also here.
Perfect. See you. Thank you.
Thank you, Sarah. Okay, so I'll just really quick make groups. Like right now, it's not just listening, sorry. We'll need to step up. And I think it's better if we create 3 groups with this arrangement. Maybe someone can come to this one, that it's the one that have less. And if you can start, I don't know, coming together in maybe the 2 tables in the middle, and I'll start sharing some of the post-its and some printing so we can start putting together this. And okay, I'll start sharing the prints. I'm going to invite 2 people from each group to present every persona. So we can start with the group in the right. Can you share, I don't know who wants to present really brief, the 2 personas?
When it works, now it works. So our team will be presented by 2 persons. One is M. Odeler, yeah, so-called with mustaches, gentleman, and his location. Yeah, Till said that you probably have to think digitally. So he proposed that cloud is the major place where nowadays modelers model things. So I kind of had to agree that indeed our local computers clusters are just gateways to somewhere else. But in principle, everyone is living already in cloud. So then, yeah, I ticked this right one so that the GIS platform is almost negligible. I don't have time to really learn about the GIS, and I also cross out it in my course that we don't do GIS and layers here. So data visualization is kind of important, but it's not as important as actually understanding that what to plot and what's behind the plots. Climate modeling software, of course, that's main tool. Communication, that's well, drawback of being so good at modeling. Sometimes we just are not good in communication often, but yeah, it is as Climate DT has room for improvements. Monitoring systems, yes, we indeed have to be aware what is actually going on. So even now I spent 50 minutes of browsing satellite images, what I promised about ice deformation for Jan. So we are really relying on very fast and very up-to-date monitoring systems, understand what's going on. So minute is over, but regarding other blocks, I would say that the money is big goal, motivation, and challenge. So, and really the communication, which is we are not very good at, is also a challenge. How our knowledge about processes, data, environment gets into the right table of decision makers, how this big data will become decisions. And of course, the challenge is that if no big data goes to decisions, there is no money. So it's all connected. Thanks.
Thank you. Can you share? You have a second persona, right? Yes.
Yes, our second user was more broadly a med service, a middle-age service, occupation forecaster, and location is probably in one of the countries, so it's an office. So about the stars, how about the motivation, the med service could apply it for GIS platforms, certainly for data visualization, and for communication and monitoring systems. So the goals would be to make both the short-term and long-term forecasts more precise, and to give more accurate communication on uncertainties. And the wider motivation is to save lives and property, of course, with better forecasts. And the use case could be the analysis of an extreme event, for example. So the dissemination experience, like the forecasters in all countries use, are the media channels. We can also use the weather application to be close to people. And of course, we have the direct channels with other authorities, so they can make their decisions and plan their actions. And what are the challenges and the pain points? So one of the challenges could be that there are too many warnings. At least sometimes people say that there are too many warnings, and that in the end, when the event happens, they are not very eager to act and react. The other challenge is to describe the impact, what the severe weather event actually can bring, and how it will impact people and their homes. And of course, the challenge is the accuracy of the forecast, especially when we are speaking about a longer forecast. So it may be wrong sometimes, may go wrong sometimes. That's very shortly all.
Thank you so much. Can we go to the second group?
We also have two personas. The first one is Maria from Barcelona. She's a PhD student in geophysics. She wants to get her doctorate and get her data digitized, finish her courses such as geophysics of snow and ice. And her use case is using the data from satellite images to look at how icebergs evolve. She has written her first paper. It's not published yet. It's in peer review. She has finished the seminar and attended a few conferences and some relevant courses. she has no idea how to use the platforms. And recently, her supervisor demanded that she join an EU project because the funding is running out and she doesn't want to be in the project, but she has no choice. And another challenge she has is that the images she's working with are sometimes distorted because there are clouds that look like icebergs, and she's quite frustrated with that.
Thank you. Can you, do you have the second one?
Okay, our second profile is extremely introvert professor of name Kalle. He's 45 years old. He's a professor at Oulu University. And his only scientific interest is solving the most obscure theoretical problems there is, like systems of chaotic nonlinear partial differential equation. He has no interest in GIS platforms, data visualization, climate modeling, communication, or monitoring systems at all. His goal is to try to solve this, which is basically unsolvable, and after that he wants to retire. His dissemination experience is to publish paper and giving lectures, but he hates giving lectures because he doesn't want to interact with people, and people don't want to take his courses because they are completely impossible and nobody ever passes.
Okay. He seems like a challenge. It's part of the part of the network.
Okay, so we have Andrew from our side, who's 26 years old and doing his PhD, and he's based in Helsinki. And so his topic is to make and do a PhD, publish papers, and do stuff in naval architecture as well, to study a bit about it. And the use cases or the goals for the study are that he needs to know what kind of vessels should be used to navigate for next 40 years or so. And other scenarios are multimodal sea ice scenarios for next 40 years or extreme winters. And he needs to find out like return periods for different number of n years of extreme winters. And his dissemination experiences, he needs to communicate with the stakeholders and scientific community. And challenges would be that he has, like the supervisor has high expectation, overly optimistic, which is usual, but yeah. And the other problems would be data availability, and because the data sets are continuously upgraded, so he would need to use the most recent and the best data set available. So that's one of the challenges, which one to choose from.
Perfect. You have a second persona?
Yeah, it would be more like a joke than.
Third part.
Yeah, it was a case of Professor King, really retired, like 85 years old. So Mr. King was a fisher from the South Baltic Sea. And yeah, he wanted to know more about the marine heat waves in the Baltic Sea to develop a kind of model for fish migration, how it evolved till now and how it will evolve in the future. So he's having a lot of ideas in his head. So it's not written, but it is having like a lot of what if, but it cannot structure them yet. So for the dissemination, he was an old professor, so I think he had a big horror in his community, and is also famous in his whole group of friends. So that's like for the beer party. And yeah, for the rest, he was asking what is climate DT, and it doesn't know really well about it yet, but it's coming.
Perfect. Thank you. Now I'll give the floor to Sarah if you want to present the persona that you made online, and then we can close.
Sure. Well, do you want to go ahead, Madalena, or do you prefer that I do it? I can't hear you, so maybe I can quickly say. We were focusing more on the specific goals and challenges that they have, but I like the way you've been presenting personas so far in the room. So I can say also that our persona is Abigail. She's a 35-year-old postdoc in London, specifically interested in forest monitoring and wants to know more about DT integration with biomass emission results. And has actually experience with GIS platforms and data visualization, but has not been using any climate modeling software so far. So needs to also learn more about this to be able to integrate DT with the systems that she's been using so far. I don't know if Madalena or Antonia, you want to add something? Otherwise. Oh, she's saying her microphone didn't work. Well, then I hope I captured it all well.
Yes. Then maybe can you present it, because I'm not sure.
Could you hear me this whole time?
Yes.
Okay.
Thank you. And I think now Madalena will be able to talk. Yes.
Yes, thank you. It seems like I have access, but the presentation was already really great for our persona. Maybe if I can go to the goals and use cases. Our persona wanted to display the satellite time series, but also have access to quick high-level simulations and show some type of vegetation parameters for her forest interest and other coronament parameters. Her use cases are to show these parameters, to compare different type of data, and also integrate with other DT use cases. For example, go further with the ice. Yeah, our persona it's not that funny as the others we've heard earlier. Her challenges are with the platform, and the frustration is great with interoperability of different type of data and platforms, with data resolutions and the training resources on the hardware. Other challenges with the training and validation of AI models she's currently running, because yes, biomass just launched and other Earth observation data are not that well indexed, let's say. And on the dissemination experience, there is the level of presentation in conferences and workshops, which it's fine, but not that much to present her actual data with stakeholders and municipalities, which may be a challenge in the dissemination.
Perfect. Thank you so much.
Thank you also.
And I think now I just took an extra minute, but I will start exploring all the different personas that you created both online and here. And I don't know, in the name of the VSC team, thank you so much for sharing, for talking. Like, this is what we want to start doing more and more. And everything is super useful for us. So I hope you don't mind, but we'll keep reaching to you to get to know you better, get to know your needs, your challenges, and also the information that you have from stakeholders. And thank you so much.
Thank you. We have reached the end of today, and now next we have the poster session. But before we go there, Rivo has chosen us place where we could have dinner. This is completely unofficial, not a part of the program. But if you want to join us, then you come to this place. I'm not sure how to pronounce that. That doesn't. Well, the second word looks like Estonian. The first word not so much. So maybe some local person knows how to say the name of this place. But yeah, at 7 at this address, close to the D terminal of the harbor, there's the website and a link. I don't know, actually, I don't know why I put the link there. It's not very useful for you there while you're sitting there. But yeah, there we have the information. Anyway, so welcome to join us if you want to have dinner after this poster session. The posters you have seen there are set up over there, so you can go there and ask questions to the presenters of the posters, but this is not like intended as a super serious scientific poster session. The posters are there mostly for conversation starters, so feel free to mingle and talk to whoever you want. So enjoy, and perhaps see you over there. We'll have some conversations and perhaps also see you at dinner, and then most certainly see you tomorrow. We're starting at 8:30 with coffee, and then the first session starts at 9 here in this same place. And also people online, thank you for attending, and see you tomorrow.